live, or otherwise I have gone through this recordings also. Sir, mass spectroscopy, LCMS, MSMS, some sessions were conducted on that. No doubt, mass spectrometry and their interpretation of mass spectrometry is somewhere difficult and some complicated also. But nowadays, all sophisticated instruments we are using for mass spectra, HRMS, MSMS likewise, and where all these instruments are supported with a very strong software, having all the database built within. And that's why nowadays interpretation with the help of software is much easier. But rather the basics of the interpretation must be known, because afterward, computer and the software can give you only information, but final approval and the final confirmation must be made by the analyst himself. So today we are not going to solve any problems and numericals based on the mass spectrometry, but to interpret the mass spectrum, what is the basic requirement, what basic knowledge is required regarding the mass spectrum. So we will go and see that particular part. We are not going in much detail about the theoretical part and the instrumental part of the mass spectrometry. Rather, we just concentrate on interpretation of mass spectrometry and what is the prior knowledge required. Okay, this is just one introductory slide, 1 or 2 slides are there. Because mass spectrometry, for what purpose we use, it is used to determine molecular mass, basically. Because if your synthetic compound is there and totally unknown to you, or otherwise any herbal extract which is purified, and then to identify the compound, when we try it for the mass spectrometry, generally the compound is said to be unknown, and we have to first find out its molecular mass rather than empirical formula, then the fragments, etc. So step by step the process goes on. So the most important part of mass spectrometry is the determination of molecular mass. And molecular mass is determined by converting a molecule into molecular ion. So typical ionization process takes place. So there are so many types of ionizations. We are not going in much detail about the theoretical part here, so just told before. But a typical ionization process, one example is given here for benzamide. When the benzamide is electronically bombarded, oxygen loses 1 electron and converts into molecular ion. So mass of the molecular ion and the mass of the neutral molecule remain unchanged, because only loss of 1 electron, which does not consider in the calculation of the molecular mass. So this is what ionization process is. Now several types of ions are produced because we are generally using very high energy for ionization. Ionization potential of the compound is somewhere else, and we are using much excess energy, and that's why readily fragmentation takes place, decomposition of the compound takes place. These reactions are so rapid that a lot of fragments are obtained, and these fragments are collected by the detector one by one in a systematic manner, and it gives you a fingerprint of a molecule. It gives you a fingerprint of the molecule. Now, this high energy electron produces a lot of molecular fragments. Maybe one fragment represents the entire molecule, and the remaining fragments may be a breakdown of the molecules into small fragments. But when the molecule gets breakdown, you may receive some positively charged ions and some radicals. But here positively charged ions of the fragments are collected at the detector, and the fingerprints of all positively charged ions appear as a mass spectrum. So this is what generally a mass spectrometry is. Okay, this is one example given for benzamide. You can see here a fragmentation pattern for the benzamide. This is a benzene ring with an amide group, and because amide group is there, nitrogen has a lone pair of electrons. Similarly, oxygen also has a lone pair of electrons. Because oxygen is more electronegative, so always ionization takes place at oxygen. So positive charge of the oxygen is there and a radical. This carbonyl group is highly unstable. It tries to stabilize itself by forming a bond with a nearby carbon, and that eliminates the amino group. This is called as alpha cleavage. This is called as alpha cleavage. So alpha cleavage is most commonly observed reaction in any fragmentation. Basically, alpha cleavage is most commonly, and that is also for amide. This is one of the identification marks. So loss of amino group takes place. 121 is the molecular mass of the benzamide. Now the second ion which is formed is less by 16, that is 105. Then this carbon monoxide is eliminated rapidly as a neutral molecule by induction. This is called as induction cleavage. There are different types of the cleavage, like alpha cleavage, beta cleavage, induction cleavage likewise. So this is the induction cleavage where carbonyl group get eliminated as a carbon monoxide and it gives a benzonium ion 77. Okay. There is one more mode of fragmentation. Instead of this carbon and nitrogen bond, carbon-carbon bond can also be cleaved. This is also an alpha cleavage. So alpha cleavage may take place on the opposite side, and if this happens, the fragment which is formed is having a mass 44. This is CONH2. So these are some possibilities. And now the spectrum is given here, spectrum of the benzamide. Here we can say 121, 105, 77, and 44 are the principal peaks or characteristics peak of the benzamide. Okay, if you see in the previous slide also, you have 121, 105, 77, and 44. So what we predicted here, the same we obtained in the benzamide mass spectrometry. So this is a pattern, and every molecule has its own pattern of fragmentation, depends upon which functional group is present, depends upon how the stability of the molecule and the stability of the product fragment is there. So there are n number of factors depends on that fragmentation takes place. So here one thing one should note that there are many other fragments. Okay, just like we are going on the previous slide. Say here 121, 105, 77, and 44 are there, but not only these 4 peaks, but there are so many other peaks present. Some are very small peaks, some are somewhat taller one, but all these small peaks are important in mass spectra, but not necessarily be interpreted every time. Generally, the functional peak or the characteristic peaks are interpreted on the mass spectrum, and once you confirm the structure, then one can go in the detailing of the small peaks. Okay, what happened, which isotopes are present, and how much is the ratio of the isotopic peak and all these things, and what these small peaks indicate. So that is just to confirm whatever you have predicted about the structure in the mass spectrum. So to confirm that structure, one can go in detailing about this. Okay. So generally, explanation of at least the most abundant ions are made in the interpretation of mass spectrum. Otherwise, hundreds of peaks are there, and that make mass spectrum somewhat difficult to interpret it completely. But before we go in the interpretation, there are 3 initial steps which should be followed one by one for interpretation, and that makes it more easy. Otherwise, if you try to interpret a mass spectrum randomly, okay, any unknown sample is there, and you have a mass spectrum of that sample, and randomly if you start the interpretation by thinking that what may be present in that and all this, that will be very, very time consuming and more complicated. But if you go simultaneously, if you go step by step by solving what may be present, so you may find your answer at the same time, it will be found in very less time. Okay, so what steps are there for interpretation of mass spectrum? The first step is always run the observed spectra against the database. Always run the observed spectra with database. Now, where is the database? Database are generally present as a library in a software. Just before I told you that all sophisticated mass spectrometers are always supported with very strong software, and the softwares have all the database of all known compounds and their mass spectrums. So if you have any unknown compound, take the mass spectrum of unknown compound and compare that mass spectrum with the database which we have in our library. And if you find that some spectrums are matching with your unknown spectrum, your search will be narrowed. Your search will be concentrated only regarding few compounds, and that will be easy to interpret the exact compound in your unknown sample. Okay, so this is just trial and error. Just to minimize the load, one can go and run the observed spectrum with the database. Then all the second step is obtain HRMS. If it is possible, of course, obtain HRMS. HRMS is called as high resolution mass spectrometry. high resolution. So simple mass spectrometry can give you the molecular masses in a whole number. But if you use HRMS, the molecular masses can be obtained in a fractions. Fractions with after decimal point, 4 or 5 fractions are there. Okay. So weight of a carbon may be noted as 12.00000. Likewise. So what happened in that? You will get an exact mass of the molecule. And there are so many importance of exact mass. You can find out the elemental composition of your unknown sample. You can find exact empirical formula. Okay, how many carbon, hydrogen, nitrogen, sulfur, oxygens are present in any given formula. Okay, or in that unknown sample. You can find out that very well. So first is you narrow your search in a limited area by matching the spectra. If spectrum matches, that will help you tremendously. But if there is no spectrum matching in the library, then leave it and go on the second option, obtain HRMS. Okay, so this will help to determine elemental composition. Third one, then follow standard interpretation procedure. Once you have a HRMS, then you can go on the standard interpretation procedure. Of course, you can go on standard interpretation procedure without HRMS also, but that will make somewhere some difficulties because there are so many molecules having similar molecular mass. And we have some example in the next slide. So these are the 3 steps. If you go one by one, your mass spectrometry interpretation might be very, very easy and that will be rapid. Okay. Now, the first option was comparison of obtained mass spectrum with a library, and I think there is no need of any discussion. That is just overlaying the spectrum on all the library. That will be taken care by the software. We don't want to do anything. Okay, and that will shortlist all such spectrum which matches your spectrum. So this second, HRMS. Why HRMS is required? Here one example is given for HRMS. If the molecular weight of a compound is 72, now that is very ambiguous. The 72 means what? 72 may be C5H12 or 72 may be C4H8. Oh, and not only these two, there are still some other compounds which represent 72. So n number of fragments are there, n number of compounds are there which represent the molecular weight 72. These 2 examples are given, C5H12 and C4H8O. But exact mass of C5H12 is 72.0939, while C4H8O is 72.0575. Now you can see the difference here. In a simple mass spectrum, both compound, which are given here as an example, both compound will appear as a molecular ion peak on 72. But in HRMS, these compounds will appear at different value. C5H12 will appear at 72.0939 and C4H8O will appear at 72.0575. Now, one doubt will again come here. Is there any probability that 2 different molecular formulas represent the same highly resolved masses or same exact masses? But that is practically impossible. That is practically impossible, and that's why mass spectrum is also called as a fingerprint of a molecule. It is also called as a fingerprint of the molecule because one molecule represent only one mass spectrum and one molecule represent only one molecular weight if it is taken in fractions. Okay, so how this fraction work and what is the importance of that, we'll go again in a further. Here again, 3 examples are given. O16, we generally consider the mass of oxygen as 16, but actually, practically, we obtain the mass 15.99491. For carbon 12, practically we obtain it is 12. And for hydrogen 1, practically it obtained as 1.00783. Because carbon appear as exactly 12, carbon is called as standard for molecular mass determination. It is considered as a standard for molecular mass determination, and all parameters are considering carbon as a standard. We make all the parameters afterwards. Okay. So software allows you computation of the formulas on the basis of these fraction masses. Now, wherever our molecular ion peak appears, that value is automatically assessed by the software, and software gives you the exact elemental composition of the molecule. But if it is HRMS, in normal MS spectrum, this facility is not available, because with the same mass, so many fractions or so many compounds can be appear. So sometimes some precursors peak or some fragmented peak or even sometimes molecular ion peak may not be present on the spectrum. Okay, our spectrum may be very much complicated, because we generally use, mostly in all spectrum, we use EI, electronic ionization technique. And when we use EI, generally we use the ionization potential much excess than all ionization potential of the organic compound. So most of the compound get ionized at lower potential, and we are using much higher potential. And that's why what happens, molecule becomes highly unstable. After converting it into molecular ion, rapid fragmentation takes place. And on the contrary, we sometimes may not get a molecular ion peak. So that will make again some difficulty in the mass spectrum interpretation, because we could not identify even molecular mass. So how to interpret the mass spectrum then? So because of that, sometimes we need to change the ionization technique from EI to CI. CI is chemical ionization. This is called as soft technique. EI is a hard technique. Okay. So sometimes we can change the ionization technique to find out the molecular masses, etc. Now, this is how exact mass and the mass defect is calculated, and what is the importance of this mass defect and exact mass in a mass spectrometry. So here one example is given. Theoretically, the mass of oxygen is 16.131919. Now from where that comes, because proton we consider as 1. The mass of proton is 1 Dalton, but it is not 1 Dalton. It is 1.0072765 Dalton. Neutron 1.00866649. And electrons, of course, we never consider electron in a molecular masses, but still they are there and they have some mass. And if you calculate the mass of the electron also, then oxygen does not have a mass 16. It has a mass 16.131919, which is rounded to 16. But what the mass of the oxygen actually obtained on the mass spectrum, the observed O16 at 15.994915. Now the difference between these two values is called as mass defect. Difference between these two values is called as mass defect. So mass defect is the theoretical value minus observed value. Okay, and mass defect is very unique for a typical isotope. It is very, very unique for a typical isotope. Its value is unique for oxygen. Its value is unique for hydrogen, unique for carbon. If you change the element, the mass defect value is very unique. And that's why this value is used as a characteristic value to identify the isotopes in the compound. Okay. So here one example is given on that only. Delta M is the mass defect. It can be calculated by the differences between theoretical value and the observed value. And in the spectrum, you can also see carbon is here. Carbon is exactly on the dotted line. This is actually mass defect. Somewhere mass defects are in positive, somewhere mass defects are in negative. These all elements which are analyzed and calculated for the mass defect, no one exactly come at 0. Only carbon is there. Carbon is exactly on the line of 0. It means carbon do not have a mass defect. The mass defect of the carbon is 0. That's why carbon used as a standard while considering the mass defects and even molecular masses. While considering the molecular masses, and you may have gone through the definition of normality, molarity, etc. Always we represent this in a mass of carbon, okay, rather than. So what is the possible formulas and how one can predict the possible formulas from molecular ion peak? So molecular ion peak predict the possible formula, but if you have a normal mass spectrometry, you may predict so many formulas for a given molecular mass. For example, for 86, molecular mass 86, you have these 4 formulas. For molecular mass 156, you have all these formulas. If you calculate the mass of all the formulas, that comes to 156. So which is our exact compound? If our mass spectrum shows us that our sample has a molecular mass 156, what it should be? So it may be one of all this compound, or even there may be some other combinations, other combinations than this. These are just representations. It doesn't mean that 156 only have these 9 compounds. So this is just a representation. It may be any other combination. So which is our exact compound? For that, here exact masses are required. Okay, this is the example. 44 is the molecular mass, and this is the possible structures of 44. But if the mass spectrum determine HRMS, of course, if the mass spectrum determine the exact mass is 44.02652, that will exactly match with C2H4O. This is the closest mass. This is the closest mass, 44.02652, 44.02620. If you have HRMS, the software will take care of this. It will assign a molecular ion peak. And once the molecular ion peak is obtained, the software will assess this molecular ion peak, and it will compare, it will calculate all the elemental composition based on the mass defects, and it will find the closest value, and which formula represent that closest value. That formula will be identified as a formula of your unknown sample. Okay, so C3H8, C2H4O, CO2, and CN2H4 all has a mass 44, but exact mass of C2H4O matches with, or it is closed with, your obtained mass, and that's why this is your unknown compound. Okay, so you can calculate it mathematically if the softwares are not available, okay, by the help of mass defects. Now come to the third step. Once you have that HRMS and you have molecular mass and you have determined the empirical formula or the elemental composition, then come to the next step, interpretation of mass spectrum. But there are some standard procedures for interpretation based on the nature of the molecule, etc. So which are the typical standard interpretation process? First, confirm molecular ion identity. Sometimes molecular ion peak does not appear on the mass spectrum. Sometimes it appears, but at so less intensity that one cannot find it easily. So first of all, confirm the presence of molecular ion peak. That is called as molecular ion identity, and it must be highest mass and odd electron ion. It must be odd electron ion, because ionization is eliminating an electron. If it is electron impact mechanism, ionization takes place by eliminating the electron, and when the one electron get eliminated, the remaining fraction, that molecular ion, always have an odd number of electrons, because one pair is disturbed now. All electrons are paired, but one electron is unpaired. So we can say this is odd electron ion. This odd electron ion generally have a molecular ion generally have all electron pair. Now use isotopic abundances and deduce the elemental composition. Then calculate the number of rings and double bonds, like what we generally call the ring rule, and degree of unsaturation. Okay, so these are the second step. First, confirm the molecular ion identity. Check whether the molecular ion peak has an odd electron ion or not. Then use the isotopic abundances, the peaks of isotopic abundances, just to find out whether the isotopes are present, how many carbons are present. Even how many carbons are present, you can find out from isotopic abundances. Okay, and this is the best way to find out the empirical formula. We'll go on one example also, and then deduce the elemental composition. Once you get the elemental composition, then calculate the number of rings and double bond present in the molecule. Okay, that is hydrogen ion deficiency, you can say, or it may be called as DBD, or it may be called as a ring rule, it may be called as a degree of unsaturation, whatever it is, but all comes similar part. Mark important ions like highest mass, the peak with highest mass, the peak with highest abundances, the peak with highest length in the group. There are groups of peaks. Okay, sometimes one tall peak is there, the taller peak is there, and some small peaks are there on both sides of that taller peak. Okay, so this whole is called as a group of peak. So you have to consider the highest peak of the group. Okay, so mark out these values Highest mass means molecular ion peak. Highest abundance means a base peak. Okay, so mark out the values of molecular ion peak, base peak, and all highest peaks from the given groups. Okay, from the mass spectrum. Then evaluate secondary and substructural assignments. Some important characteristic ions are there. Okay, for example, in aldehyde, the loss of hydrogen is very, very characteristic. In case of any aromatic compound, the benzonium ion or phenyl ion is one of the best characteristic. For alcohols, the loss of water is the best characteristic. So you can just concentrate on the mass spectrum and try to find out the important characteristic ions, or sometimes important characteristic radicals also plays very important role. Okay, so find out that. And last one, that postulate a molecular structure. Now you have all the data. You have molecular mass, you have empirical formula, you have degree of unsaturation, you have a characteristic peak with you, and you have some characteristic ions which are either left or appear on the mass spectrum. Okay, so either radical or ion. So now try to combine all this, compile all this data which you have and form a molecular structure. Once you form a molecular structure, then just to confirm that molecular structure, now you can concentrate on a smaller peaks in the mass spectrum. So this part comes afterward. So always interpretation of mass spectrum is done with the principal peaks, larger peaks, and then for confirmation only, we go on the smaller peaks. Okay, so this is again one of the example. If compound contain no nitrogen or even number of nitrogen, generally the molecular ion gives you even mass. And if there are odd number of nitrogen, then the molecular ion generally gives you odd mass. This is universal rule, and this is called as nitrogen rule. This is called as nitrogen rule, a universal rule. You can cross check all this. Some examples are also given. Water, no nitrogen is present, 18 mass. Methane, no nitrogen is present, 16 mass. But you can see the last two, NH2, diamine. No even number of nitrogen present and mass is even. Then C5H6N2. Again, even number of nitrogen present and mass is even. On the contrary, if you have ammonia, odd number of nitrogen, the mass is 17. Okay, C9H7N, the last example, C9H7N, odd number of nitrogen, 129, odd number of mass. This is called as nitrogen rule. If you have a molecular ion, and if you have a molecular ion peak on the mass spectrum, just see the value of molecular ion peak. If it is odd, it indicates either one nitrogen is present or any odd number of nitrogen is present in the given spectrum or a given sample. Okay, or otherwise, if it is even, then either it is having no nitrogen or even number of nitrogen. Okay, so that will generally narrow your search for the chemical structure. This is called as nitrogen rule. Now, this rule is hold for all compounds. This rule is hold for all compounds. Okay, like carbon, nitrogen, oxygen, sulfur, X, P, B, Si, As, and alkyne earths. Okay, you can apply this nitrogen rule in presence of any element present in the molecule. Okay, the nitrogen rule always obeys by the compounds, organic compounds. So as a consequence, for the fragmentation at a single bond, even number of molecular ion will give odd number fragment. Now this is very, very important to identify whether the last peak on the mass spectrum is really a molecular ion peak or not. Okay, just before I told you that a molecular ion peak sometime appear on the spectrum. Mostly it appear on the spectrum, but sometime it may be missing. Sometime it may be missing. And one of the best example is higher alcohols. Higher alcohols where molecular ion peaks are generally missing. So last peak we consider as a molecular ion peak, and where our interpretation goes wrong, because it is not a molecular ion peak. It is a peak which is second than the molecular ion peak. Okay, a fragmented one. So first you have to identify that last peak given on the mass spectrum, is it really a molecular ion peak or something else? So to identify that, one correlationship always keep in mind that molecular ion, if it is even, just like in previous slide, we have methane, okay, CH4, 12 plus 4, 16. So methane is 16, an even number. So if your molecular mass of the molecule is even, then it always gives you odd number of fragments. Okay, the mass of the fragment is always odd. And if your molecular ion has a odd weight, then it generally fragmented in the even masses. Okay, so this is always takes place in most of the compound. But if the nitrogen is present, this should be considered that all nitrogen should be present in one fragment. All nitrogen should be present in a fragment. Fragment means positively charged ion. Here, fragment doesn't consider radical. Fragment consider only ions. So even number of molecular mass always gives you odd number of ion. Odd molecular mass always gives you even mass of the ion. And if nitrogen is present, generally all nitrogen, maybe 1 nitrogen, 2 nitrogen, 3 nitrogen, whatever the nitrogen is present, all nitrogen should be present in the ion. It should not be present in a fragment. Okay, if this happens, we can use the molecular mass and its fragmentation, the next fragment, as a source of identification of the molecular mass ion or molecular ion peak. Okay, now we'll go on one example also afterward. This is ethyl, CH3, the mass is 30. Ethyl mass is 30. Now after fragmentation, this gives you 15. See, even mass gives you odd fragment. Here the second example is dimethylamide. The mass is 45. Okay, it obeys the nitrogen rule, no doubt. The mass is 45. Odd mass get fragmented into even fragment. Okay, CH3NH. Now, what happened? Sometime the induction cleavage takes place, and due to induction cleavage, this NH appear as a radical. So CH3NH positive charge is a fragment, and CH3NH radical is not a fragment. It is not a fragment. This is considered as a fragment, CH3. So fragment should contain nitrogen. Okay, according to rule. So this is, if this happens, then only this obeys the law. Here 45 mass gives you 15 fragment. So both are odd. Here it disobeys the law because nitrogen is not present in the fragment. Nitrogen is present in the radical. So this should be kept in mind always. Otherwise, this is very, very easy. Now come to the next part is rule of 13. Nitrogen rule is different. Nitrogen rule is used to find out whether nitrogen is present or not, and if it is present, whether it is present in even numbers or odd numbers. Okay. Then second is the rule of 13. Rule of 13 is good applicable for carbohydrate, good applicable for hydrocarbons. Okay, hydrocarbons where only carbon and hydrogen is present, maybe saturated or unsaturated. That doesn't matter. But if it is hydrocarbon, you can apply rule 13. Now, what is rule 13? If you divide the mass of the molecule by 13, if you divide the mass of the molecule by 13, the quotient of that division, always represent the number of carbons present in that molecule. And the quotient plus remainder generally represent the number of hydrogens. Okay, and that's why we write CQ. CQ means quotient, HQ plus R, where Q stand for quotient, R is remainder. Okay, so rule 13 always obeys this CQ, HQ plus R. Right? Now this is one example. 78 the mass. 78 the mass. From this 78 mass, you can find out the empirical formula. 78 divided by 13, that is 6, and remainder is 0. 13 6 are 78. Remainder is 0. So the formula is C6H6. The formula is C6H6. But if your mass is 92, divide that 92 by 13. 13 sevens are 91, and remainder is 1. Remainder is 1. So it is 13 sevens are, means C7H8. C7H8 is the molecular formula. So you can Find out the molecular formula, empirical formula, or carbon and hydrogen ratio. You can say elemental composition if only carbon and hydrogens are present. Okay, elemental composition with the help of rule of 13. Okay, but what? Can you apply this rule of 13 on alcohols or on amines? Of course, yes. If you know that alcohol is present in your compound, that functional group determination should be done prior. If you know that your compound is alcohol, OH group is present, then you can apply this rule 13 on that by eliminating the mass of oxygen from the molecular mass, and then apply the rule of 13 to get number of carbon and hydrogen, and then add one oxygen in that. That's it. It's too easy. Okay, you can apply it with the amines also, and similarly. So this is what rule 13 is. Now this is one of the mass spectrum, and we have to determine whether the given mass number 256 is a molecular mass or not. 256 is the last peak. Okay, these are isotopic peaks. The largest peak is 256. Okay, from this group. So whether 256 is molecular mass or not, to identify that, first take a look on the adjacent peak. Adjacent larger peak is 226. 256 and 226. What is the difference between this? Is 30 AMU, 30 Dalton. Okay, so loss of 30. The loss of 30 mass indicated here. So mass loss is also okay. The mass loss is also okay. And even molecular ion is given even fragments. Even molecular ion is giving even fragment, and this is not possible. This is not possible. That's why 256 is not a molecular ion. 256 is not a molecular ion. Okay, so generally the largest peak we consider as a molecular ion from the given group, the last group. Okay, so here somebody may consider 256 as a molecular ion, and he may try to interpret the mass spectrum by considering 256 as a molecular ion, but the interpretation will go wrong because the next peak is 226. So the loss of 30 can be suggested, but even mass never gives you even fragment. And that's why this is a wrong molecular mass. Molecular mass may not be appear on the mass spectrum. It may be somewhere here. It may not be appear on the mass spectrum, but this is not a molecular mass. So this is the way to identify the molecular masses. This is second example. Here 256 is even molecular mass, but it gives you a fragment at 177, the loss of 79. Now you can see here, even molecular mass gives you odd fragment. Means this molecular mass is correct. This molecular mass is correct. Okay, so 256 can be considered as a molecular mass. And what are these peaks? After the molecular mass, this may be an isotopic peak. This may be an isotopic peak because the total group is there. This is the group of ions. This is the group of the peaks. And from this group of the peak, we have to consider the molecular ion peak. Okay, so that is 256. Okay, so this is the correct molecular mass. Then in this, you can see also, and theoretically it is correct. 305 is an odd molecular mass. It should give you even fragment, and you are receiving an even fragment, 268. See, but how much mass is lost? 37. 37 mass lost is unlikely loss. These are unlikely losses. 4 to 14, 21 to 25, 33, 37, 38. These masses are never get escaped from the molecule. These are most unlikely masses. And that's why this loss 37 indicate that this loss is not good. This is unlikely. And that's why this is not a molecular mass. This is not a molecular mass because it is giving out 37 loss. And 37 loss is unlike losses. That's why it is not a molecular mass. So in this way, one can try to identify whether molecular mass appear on the spectrum or not. It may appear in, mostly it appears, but sometimes it may not appear on the mass spectrum. And that's why before starting the mass interpretation, one should know and one should identify the molecular ion peak. Okay. So this is, these are a few examples. Now, second, intensity of the molecular ion peak. Molecular ion peak may be present on the spectrum, but is it small or it is tall? The intensity of the molecular ion peak plays very important role, and that will narrow your search regarding your unknown molecule. Okay, now how do it helps you? Stability plays a factor in whether or not we see the molecular ion. Okay, now these are three different conditions which we have compared in between. Decreasing ability to give a prominent molecular ion. Some molecules are there which gives you prominent molecular ion. Okay, so there is no difficulty in identifying the molecular ion peak. So that is much prominent. Okay, so here aromatics gives you the tallest peak, molecular ion peak. Then conjugated alkene, followed by cyclic compounds, then organic sulfides, alkane, and mercaptins. All these are the compounds which gives you comparatively higher molecular ion peak. There are some molecules which gives you smaller molecular ion peak, but these are recognizable. You can recognize that this is a molecular ion peak. Means that much height is there, which can be recognized. Like ketone, amine, ester, ethers, carboxylic acid, like aldehydes, amide, halides, they are all in the same lane. So they have less intensity of the molecular ion peak, smaller molecular ion peak, but after all, it is recognizable. But some molecules are there, some types of the compounds are there which do not give you molecular ion peak, or although if it is appear on the mass spectrum, it is non-recognizable. It is non-recognizable practically. So like aliphatic alcohol, nitrites, nitrile, nitrates, nitro compounds, highly branched compounds, all these are molecular ions or the molecules which either does not give you molecular ion peak or gives the molecular ion peak but non-recognizable. Okay, it is so small. So identifying the presence or absence of the molecular ion can sometimes problematic just because of those type of ions which gives you very small peak or non-recognizable peak. And last one is the prior knowledge of the functional group present in the molecule helps to identify the correct molecular ion. Okay, if you know that your molecular ion is, if your molecule is aldehyde, it will help you to find a molecular ion peak. If you you can identify the molecular ion peak easily because that should be a tallest peak. Okay, so you can take the help of the previous chart and the known functional group to identify the molecular ion peak. Now come to the next part is degree of unsaturation. It is also called as DB, or it is also called as ring rule, etc. So degree of unsaturation is calculated, and for ethylene, it is 0, for propylene 1, for cyclohexane 1, for this compound is 7. Okay, because say degree of unsaturation indicate either double bond is present in the compound or triple bond is present in the compound or some rings are present in the compound. And if you know the molecular formula, you can calculate this degree of unsaturation easily. Okay, by this formula. dB is equal to C minus H by 2 plus N by 2 plus 1. If you put your molecular formula, number of carbons minus number of hydrogen divided by 2 plus number of nitrogen divided by 2 plus 1, it will give you some value. This value tells you about what is the degree of unsaturation of the molecule. Okay, for example, now this molecule 1 number has dB value 1. For 2 number, the dB values are 2. Okay, for 3 number, the dB value is 1, because again carbonyl group is present, means 1 double bond is present. Okay, so you can just find out here 2 rings are present. Here 2 rings are present, so dB is 2. Here 3 rings and 1 double bond is present, so dB is 4. Okay, 3 rings for 3 and 1 double bond means 4. Okay, and for this compound, this trinitro phenyl and methyl group, so toluene, trinitrotoluene. For this compound, you have a benzene ring and 3 double bonds. Means benzene ring means a ring and 3 double bonds. Okay, with nitro groups are there. So in nitro groups also N double bond O are there. Okay, so these 3, 4 plus 3, 7. So this compound gives you 7 dB. You can try to calculate this by putting the values on C minus H by 2 plus N by 2 plus 1, you will find the value comes to 7. Okay. So this you can calculate the degree of unsaturation, and it gives you some rough idea about how many unsaturations might be present in the molecule. Okay. And that at the time of determining the structure, that can help you. Now come to the next point, isotopes. In interpretation, this is also one of the most important point, because here you can find out how many carbons, hydrogens, oxygens, and even some isotope compounds like chlorine, bromine, okay, whether they are present and how many of these are present. Okay, so you can even find out the molecular formula also by isotopic peaks. So there are 3 isotopic peaks which are very important to analyze. One is M+1. M+1 means M is the molecular mass and +1 is its isotope. Okay, like carbon has mass 12 and carbon 13 is the isotope whose mass is 13. So the mass is greater by 1. Okay, then like chlorine and bromine, they have a second type of isotope, M+2, because there are two isotopes of chlorine, chlorine 35, chlorine 37. The difference in the masses is by 2. Likewise, bromine 79 and 81. The difference is 2. Okay, and one more category is there. That is a combination of chlorine, bromine. If present in the given molecule, you may assess M+4 peak also. M+4. Okay, so we'll take one example here. M+1 from 1.1% height intensity with respect to the molecular ion peak for C13 in nature. Okay, this is a characteristic for C13 or isotope of carbon. All isotopic peaks generally appear for every carbon 1.1% height of the original molecular ion peak. Okay, what this indicate? If your molecule has only one carbon, like methane, so molecular ion peak of the methane is obtained, and a very small peak which represent 1.1% height of the molecular ion peak, that will be followed by the molecular ion peak just after that. So at M+1 value, so height of that peak will be 1.1%. But if you have 100 carbons in a molecule, then isotopic peak may have a height of 110% than the molecular ion peak. Means isotopic peak may have higher value or higher, or isotopic peak may be taller than the exact molecular ion. Okay, so this is generally a number of carbon atoms. Now, how it can helpful? You can see here a molecular ion peak appear at 78, and its M+1 peak appear at 79. Okay, this is one of the example, and the height of this 79 peak is 7% than the height of 78. Height of 79 peak is 7% than the height of 78. That one can measure from the mass spectrum directly. So how many carbon may be present in that? So 7% intensity, this is the formula. Number of carbon into 1.1 is equal to 7%. So how many carbons are there? 7 divided by 1.1, 6. So this molecule whose molecular ion peak appear at 78, whose isotopic peak appear at 79 with intensity of 7%, that compound must have 6 carbon. That compound must have 6 carbon. Similarly, you can calculate for H1. Similarly, you can calculate for oxygen, nitrogen, sulfur, etc. So this isotopic peak and its height of the isotopic peak, ratio of the isotopic, actually very, very important. Okay, this is actually very, very important. Second example is isotope M+2. Okay, in isotope M+2, 2 examples are given: chlorine and bromine. Chlorine has 2 isotopes, 35, 37. Bromine has 2 isotopes, 79, 81. But if you compare between chlorine and bromine, you may find if chlorine is present, the isotopic peak and the main molecular ion peak may have a ratio of 3:1. This is the main peak and this is isotopic peak. It has a ratio 3:1. Okay, actually the ratio is 75.8 as to 24.2. But if you round it up by 75 and 25 approximately, so that is 3:1. Okay, and for bromine, the height is nearly equal. It is nearly equal. So that is 1:1 height. Okay, bromine always indicated on the mass spectrum by molecular ion peak. So there are two peaks, one on M and second is M+2, and the height of both the peaks are always equal. This looks like a doublet, and that is the characteristic identification of a presence of bromine. But what? Instead of single chlorine and single bromine, if multiple chlorines and multiple bromines are present in the molecule, can you identify it by the isotopic peak? Of course, you can identify it, and this is the chart which gives you the pattern of isotopic peak if multiple chlorine, multiple bromines are present and their combinations are present. If any one of this pattern appear in your mass spectrum, then you can directly confirm how many chlorines and how many bromines are present. Okay, now these are given in the literature, no doubt, and these patterns you can even calculate. You can even calculate according to their ratios and the probabilities of how many chlorine and how many bromine will appear and where it will appear. Okay, so based upon that and based upon their weights, the molecular masses, we can get these probabilities, and such ratios of different halides, chlorine, bromine, and their combinations are available in the literature, and one can just refer that literature to find out how many chlorine and bromine is present in given molecule. Okay, so this is the most important application of the mass spectrometry. So you can identify the presence of chlorine and bromine very easily with their proportions. Now there are some factors which may influence the ion abundances. You might have seen that in mass spectrometry, some peaks are smaller, some peaks are taller. Now, why some peaks are taller, why some peaks are smaller? Because all peaks indicate the ions. All peaks indicate the ions. But some ions are less abundant, some ions are more abundant. Okay. Some ions are less abundant, some ions are more abundant. Okay. Now, which ions are more abundant? The ions which appear with a taller peak. They are called as a more abundant ion. And the peaks which are very small are called as less abundant ion. Okay. So which factor make the stability of the ion to change? So these factors are electron sharing stabilization, resonance stabilization, diastonic radical ions. Okay, that is separation of charge. That is called as separation of charge and radical. Sometimes charge and radical is present on the same atom, but the separation of the charge and radical takes place due to the resonance, and this separation stabilizes the ion. Here one example is given, CH3, CH2, CH2, CHO, where radical and positive charge is present on the oxygen. But this will be converted into a sort of McLafferty rearrangement. You know, this is a alpha carbon, beta carbon, and gamma carbon. This is carbonyl group. So a hydrogen from a gamma carbon get abstracted by the oxygen and it becomes CH2 radical. CH2, CH2, CHOH plus. Okay, this is McLafferty rearrangement. So this compound, this molecular ion undergo McLafferty rearrangement, and it gives you a fragment. Oh, okay, mass is same, but this gives you a fragment which is more stable. So this fragment is more stable. Stability of the fragment, stability of the ion based on these three characteristics: electron sharing, resonance stabilization, and separation of charge and radical sites. Okay. One more factor is there, Stevenson's rule. This indicates that when any compound undergo fragmentation, for example, ABCD is there, it undergo fragmentation A plus BCD radical or A radical plus BCD plus. So there are two radicals, BCD and A. In one fragmentation, BCD radical is formed. In second fragmentation, A radical is formed. Which radical will form with a higher abundances? That indicate which radical has highest ability to retain the unpaired electron. Which radical has a highest ability to retain unpaired electron? So that will be formed at higher extent. And if BCD has a higher ability, then BCD will form at a higher extent and the peak of A plus will be taller. The peak of A plus will be taller. And if A has more ability to retain, then the peak of BCD will be taller. Okay. So this is how this affect the Stevenson's rule may affect the height of the fragment peaks. Okay. Now there are some exceptions of the Stevenson rule also, and this is one of the best example of exception of Stevens rule, that carbocation, the stability of carbocation. Tertiary carbocation is more stable, and that's why it will appear rapidly. So this will appear on the mass spectrum as the tallest peak, and methyl carbocation will appear as the smallest peak. Okay, but radical which is eliminated for this, it does not obey the Stevenson's rule. Okay. Next factor is the stability of the neutral product. Sometimes the fragmentation gives out the neutral product. Now, how stable the neutral product is? If the neutral product is more stable, the fragmentation will take place at higher abundances, and that's why the peak will appear. Peak for the ion will appear at taller at a higher abundance. And if the neutral product has less stability, then the peak will be smaller. Okay, of course, peak does not appear for the neutral molecule. Peak appear for the remaining ion. But because the stability of the neutral molecule is more, that type of fragmentation takes place rapidly, and more abundances are there to appear for that ions. Okay. So these are generally losses 2, 16, 18, 28, 30, 32, 34, 36. These masses generally get lost from the molecule because they generally represent the neutral molecules. They represent neutral molecules. The next factor is entropy and steric effect. Steric effect and entropy. Now, this is one of the example here. Para-amino toluene, or you can say it is para-amino benzyl cation. Okay, it's benzyl cation. Para-amino benzyl cation shows the resonance, and because it shows the resonance, generally this gives you very stable ion, NH2 double bond, and this resonance will arrange these double bonds automatically and double bond CH2. Okay, so because of this resonance, which is possible in the structure, this ion is very stable, and the molecular ion peak will be very strong. Okay, in this case. So this is what about steric effects. Similar steric effects are present in various compounds. Okay. Now, what are the basic fragmentation mechanisms? This is one of the last part in interpretation, so which should be known. Okay, basic fragmentation mechanism should be known, because any molecule get fragmented, although it fragmented rapidly, but it always get fragmented by certain mechanism. And if you are strong in the organic chemistry, you may think about these mechanisms of the molecule to get fragment. Okay, but generally, which mechanisms are important? Sigma cleavage. Sigma cleavage is very important for fragmentation. All hydrocarbons generally get fragmented by sigma cleavage only. There are so many other compounds. Saturated compounds generally get fragmented by sigma cleavage. Okay. Even sometimes unsaturated compounds also get fragmented by sigma cleavage. Second is alpha cleavage. But alpha cleavage with homolytic radical site initiated. Homolytic alpha cleavage means radical site initiated. And inductive cleavage is also there. Inductive cleavage, where the transfer of 2 electron takes place rather than a transfer of single electron. Okay. And fourth is multiple bond cleavage. In McLafferty rearrangement, you may see that more than one bond is broken at the same time of fragmentation. Okay. So multiple bond cleavage. These are 4 basic mechanisms: sigma cleavage, alpha cleavage, inductive cleavage, and multiple bond cleavage. Now we'll see one by one what is sigma cleavage is. Generally, a removal of electron from sigma bond via electronic ionization weakens the sigma bond. Okay, any sigma bond which loses the electron makes the sigma bond weaken, and that becomes a site of cleavage. That becomes a site of cleavage. Now, cleavage of a single bond in an odd electron molecule, that is M plus, must produce an even electron. So that we have seen earlier. Odd electron molecule generally give you the even electron fragment. Okay, when if the sigma bond cleave. So cleavage of single bond, cleavage of sigma bond generally obeys that rule. Odd electron molecule gives even fragment, even electron molecule gives odd fragment. Okay. As bond breaks, one fragment get a charge and one fragment remain as a radical. Okay. So because this is single bond, when the bond get open, one fragment always deals with the electron, free electron, that is called as radical, and one fragment always take a charge away. Okay. And the other fragment is charged. Highly substituted carbocations are more stable. See, the carbon which is more branched, that is liable to break. That is liable to break because when that bond breaks at the carbon becomes carbocation. And tertiary carbocation is most stable. And that's why largest branched carbon is susceptible to cleavage. Is susceptible to cleavage. And we have some examples also regarding that. Last one is long N-alkane chain tend to produce many fragments separated by 14 Dalton. Okay, if you have a carbon chain, alkane chain on one side of the molecule, and that is a comparatively long chain, then generally you will get several peaks on the mass spectrum at a distance of 14 mu, at a distance of 14 Dalton. Okay, in the range of 20 to 90. Now, this is one example of one bond cleavage. Carbon-carbon bond can be cleaved. Now, here you can see the arrow showing only one head. Arrow is showing only one head. This is called as fish hook head. This is called as fish hook head. Okay. So, when such arrows are shown, this indicate the transfer of one electron. This indicate the transfer of one electron. So, this carbon-carbon bond breaks and it gives you one cation and one radical. Okay. Where carbon and heteroatom will cleave, when such atoms are cleaved, generally heteroatom takes a radical away and carbon bears a positive charge because heteroatom may be a chlorine, heteroatom may be a nitrogen, heteroatom may be sulfur. Those are electron loving. Because they are electron loving, mostly they take the electron with them and appear as a radical. Okay, and peak of the carbocation will appear on the mass spectrum. So this is called as fish hook transfer or fish hook arrow that indicate the transfer of one electron. But if two electrons are transferred from one atom to another atom, it should be denoted by a complete arrow. This is two-barred arrow, complete arrow. This is one of the example where molecular ion peak is missing. You see, just before I told you, molecular ion peak may not be possible or may not be appear. Now, this is the example of neopentane. This is neopentane, molecular mass is 72. Okay, but this 72 peak is missing here. You can see this is 70, this is 80. There is no peak in between 70 to 80. 72 peak is missing because this is highly branched carbon, and highly branched carbon is so stable for its ion that it rapidly eliminates a radical. It rapidly eliminates a radical. This reaction takes place here. The tertiary carbocation is formed and methyl radical is eliminated. So this is called as M minus 15. Elimination of the mass 15. M minus 15, that is 72 minus 15 is 57. You will get a base peak on 57. This is not a molecular ion peak. This is base peak. Molecular ion peak is somewhere here 72. Okay. Now, how one can identify this is base peak? The next tallest peak is 41. The next tallest peak is 41. 57 is an odd and 41 is also odd. Odd never gives fragment into odd. Odd never gives fragment into odd, means this is not a molecular ion peak. This proves that the peak at 57 is not a molecular ion peak, rather this is a fragmented peak and molecular ion peak is missing. Okay, so this is the way how one can identify molecular ion peak. Okay, this is second example. This is N-pentane. In N-pentane, most likely elimination takes place for ethyl radical. Most likely elimination takes place for ethyl radical, and the mass of ethyl radical is 29. The mass of pentane minus 29 will be the base peak. See, this is 57. This is mass of pentane 86. Okay, and when 29 is subtracted from this, the 57 is the base value because this is most likely fragmentation for N-pentane. Okay. This is branched carbon. One more example, branched carbon. Now, because the branching is here, you have three alpha bonds for the branched carbon. One alpha bond is here, second alpha bond is here, third alpha bond is here. Okay. Now, if alpha cleavage takes place, it will take place in all the three directions. But elimination of the longest radical is generally takes place. Elimination of longest radical generally takes place. Now here, if elimination takes place here, the radical is methyl. If elimination takes place here, the radical is methyl. But if elimination takes place here, the radical is propyl. So most common fragmentation site is CH and CH2 bond here. Okay, that will eliminate the propyl radical, and this ion will appear at mass 43. You can see the abundance of this 43, the tallest peak. Why? Because it eliminates the largest radical. Okay, elimination of largest radical is most favored than the smallest radical, right? So this is explained here. You can see here elimination of methyl radical. Elimination of methyl radical gives you 71 peak. Okay, gives you 71 peak, and 71 peak is smaller than the 43 peak. Okay, 43 is the longest peak and 71 is smaller peak, because this type of fragmentation at this alpha bond is less favored than this alpha bond. Okay, so this is regarding one sigma cleavage. Now there are some helpful rules also for fragmentation. Even electron ion rarely cleave in odd electron fragments. Okay, even electron ion means positively charged ion without free electron, without unpaired electron, that is called as even electron ion. That is rarely cleaved in an odd electron ion. Okay, but odd electron ion can be cleaved in even electron ion. So this is represented in some examples also. Order of carbocation is always tertiary with allyl or secondary, then followed by primary, then methyl, and then hydrogen. Then loss of the longest carbon chain is always preferred, that we have discussed just before. And fragmentation ion stability. Fragment ion stability is more important than the fragment radical stability, because mass spectrum deals with ions. It doesn't deals with fragments, radical. Okay. So after fragmentation, you have one radical, you have one ion. Mass spectrometry deals with ions, and that's why stability of the ion is more important than stability of the radical. So what Stevenson say, stability of the radical depends upon the stability of the radical and ionization capability of the radical, the fragmentation takes place. But that Stevenson's rule can be overcome, and that can be disobeyed, because in mass spectrometry, it is a fingerprints of the ions, not the radical. One can say the stability of the ions are more important than stability of radicals. Come to the second point, alpha cleavage, homolytic cleavage. Sigma cleavage we have seen. Alpha cleavage means somewhere functional group is present. The first carbon from the functional group is called as alpha carbon. The cleavage of the bond between alpha carbon and a functional group is called as alpha cleavage. Okay. So in homolytic cleavage, what happened? The new bond formation start with a radical. New bond formation start with a radical, because with the electronic impact, suppose one electron is lost by the molecule convert into molecular ion, that free radical is unstable. It try to form a bond with a neighboring carbon. It try to form a bond with a neighboring carbon. Here in this picture, you can see this radical gets shared by the Z with the neighboring carbon, but carbon don't have its own radical. So it takes a radical from the neighboring bond. It takes a radical from the neighboring bond and shared with Z. So that will give you C double bond Z. This C double bond Z is the ion. Okay, because radical is utilized by the Z. So C double bond Z is the ion. But what about this carbon? This carbon takes its own radical away. So this part of the molecule appear as a radical, and this part of the molecule appear as an ion. This is called as alpha cleavage. Okay, this is functional group. This is alpha carbon and this is alpha bond. So the cleavage between alpha and beta carbon takes place. This is called as homolytic cleavage. The name homolytic cleavage can be explained very well by radical site driven. So here radical is responsible to form a new bond, and this cleavage is driven by the radical itself. That's why it is called as homolytic cleavage. Okay. Now here carbon has a radical. Here carbon has a radical. So carbon shares this radical with a neighboring carbon, and on the contrary, carbon said CZ bond splits. CZ bond splits, and here it gives you Z ion with a radical. Z ion with a radical, and it gives you a neutral compound. C double bond C is alkene, a neutral compound. Okay, so such type of cleavage are possible. All these are alpha cleavage or homolytic cleavage. Okay, this mechanism is also called radical site initiating cleavage. Charge does not move in this reaction. Charge remain on the carbon, so it will remain on the carbon. If charge remain on the heteroatom, it will remain on the heteroatom. Charge doesn't migrate. What migrate is radical, because radical gets shared. Radical gets shared, and that's why initially radical was on Z, but after fragmentation, you will find the radical is on carbon. Okay. If the initially radical is on carbon, after fragmentation, you will find the radical is on Z. So radical get migrate. Charge never get migrate. Okay. Alpha cleavage directing atoms are nitrogen. Generally, if nitrogen is present, this type of cleavage is definitely happen. Definitely, alpha cleavage directing atom, the most directing atom is nitrogen, followed by sulfur, oxygen, then R. Okay, nitrogen and R, and followed by chlorine, bromine, and followed by hydrogen. Okay, so all these are what we can say directing atoms. You can say from highest to lowest. Then loss of longer alkyl chain is often favored, and this is always common for all. Longest alkyl chain generally get eliminated. So loss of longer alkyl chain is often and most commonly favored. And energetic of both products. Energetics of the product which is generated after fragmentation plays an important role. Okay, so charge and the neutral compounds. That energetics plays important role for the stability. This is one example of alpha cleavage. Alcohols. In alcohols, what happened? RCH2COH. Okay. Now, this is alpha bond. The cleavage at the alpha bond may take place, and that gives you the radical RCH2. Because here oxygen possesses a radical and the charge both. Oxygen possesses a radical and the charge both. In alpha cleavage, charge doesn't migrate. Only radical migrates. So whatever is remaining fragment is, that takes a radical away, and the charge remains with oxygen or carbon. So that dislocation of the charge, we can say a local dislocalization of the charge from positive, from oxygen to carbon, because these are attached directly. Okay, so they are in the resonance. This is example of mass spectrum for CH3, CH3, CHOH, CH2, CH3. Okay, this is 2-methyl-3-pentanol. In this case, the most branched carbon is here. The most branched carbon is here. These two are the most branched carbon. So fragmentation, of course, takes place between these two. If fragmentation takes place between these two, there are chances that CH3, CH3 positive ion will be eliminated, or otherwise CH3, CH2, CH double bond OH positive ion will eliminate it. Okay, means either this ion is formed or this ion is formed. So you may take two peaks, one peak at 73 and second peak at 59. 59 peak represent CH3, CH3 positive ion, and 73 peak represent CH3, CH2, CH double bond OH positive ion. Okay, so this is the way one can just go through this mass spectrometry and the alpha cleavage. Okay, this is 2-butanone, etc. And we have a lot of examples here, but because we have very limited time, so we'll go on the next point here. Alpha cleavage is all common, only multiple examples are given just to understand what is alpha cleavage is and how it works. Now, next is heterolytic cleavage. Heterolytic cleavage and alpha cleavage, these are differ only in how cleavage initiated. In alpha cleavage, the cleavage initiated or the formation of the bond and breaking of the bond initiated by the radical. But here, it is charge driven. It is charge driven. Positive charge is responsible for the migration of the electron, not radical is responsible to form bond. And this is the basic difference between heterolytic cleavage and homolytic cleavage. Homolytic cleavage is called as alpha cleavage. Heterolytic cleavage is called as charge-driven cleavage or inductive cleavage. This is also called as inductive cleavage. Okay. Now, charge site induces a pair of electron to migrate. Suppose after fragmentation, carbon possess a positive charge, or oxygen possess a positive charge, or any element in the molecule possess positive charge. That positive charge element induces a pair of electron from the neighboring carbon or from the neighboring atom, whichever the atom is. Okay, so that positive charge initiate the movement of electron, but in pair, not a single electron. So this is called as inductive cleavage. The charge migrates to the electron pair donor, where even electron fragment can further dissociate by this mechanism. See, just before we told that even electron fragment does not dissociates into odd electron fragment generally. Okay, and generally even electron fragment do not show fragmentation further because they need high energy for the fragmentation. But due to the inductive cleavage, even electrons fragment can also be fragmented into smaller fragments. Okay, so some examples are there. We will go on that. Inductive cleavage directing atoms are as follows. Halogens generally shows highest inductive cleavage because these are electron loving. Halogens are electron loving, so they generally take the pair of electron rather than a single electron. They abstract a pair of electron, okay, and give out the positive charge to the remaining fragment. Then followed by oxygen, followed by halogen is oxygen, sulfur. Followed by oxygen and sulfur, there is nitrogen and carbon. Okay, so you can just compare between that. Alpha cleavage is more favored when nitrogen is present, while heterolytic cleavage is more favored when halogens are present. So now for studying the fragmentation and for interpretation of the mass spectrum, if your compound shows alpha cleavage, mostly it may contain nitrogen. But if the peak is tallest, that peak intensity is also important. But if it shows inductive or the charge driven fragmentation, then possibly your compound may contain halogens. Okay, so these are some inferences. This is one of the example, inductive cleavage of 1-bromobutane. This is 1-bromobutane. See here, bromine has a positive charge and a radical on it. But because it is electronegative and electron loving group, it is electron withdrawing group, you can say, instead of taking its own radical with it, it takes 2 electrons from the neighboring carbon. So carbon will become deficient in the electron and that will carry a positive charge. So this fragment carries positive charge, and bromine with 1 electron, the positive charge will get nullified, but on second electron that will remain as a radical, unpaired electron. Okay, so this is called as inductive cleavage. Here instead of 1 electron, 2 electrons are migrated and that will cleave the molecule. But here positive charge is migrated from one atom to other atom, from one element to other element. Okay, radical doesn't migrate it. So this is what the molecule is. Now bromine can be identified. See, 136 double peak is there. At 136 double peaks are there, and this is identification mark for presence of bromine. These are isotopic peak, M and M+2. Okay. Inductive cleavage of 3-pentanone. This is 3-pentanone. Now inductive cleavage takes place. 2 electrons must be migrated towards oxygen. But from where? Now there are 2 possible sides, either from this side or from this side. There are 2 possible sides. If it takes from this side, the ethyl radical will be eliminated, and from this side also ethyl radical will eliminate it. So the product is same, and the product is same, that is 57. The mass 57 appear as CH3, CH2, C triple bond O. Okay, and this CH3, CH2 will remain, from this side, so it will remain as a radical. So 86 minus 29, that is 57. This is one of the example again. Now, how the cleavage takes place. It is observed in this way. This is one more example, 3-pentanone for 86, how cleavage takes place. Now here, if you see in the cleavage, first the charge is transferred from oxygen to carbon. First, the charge is transferred from oxygen to carbon, and then carbon takes 2 electrons. Carbon takes 2 electrons and shared it with the oxygen, and that will break this alpha bond. Okay, this is actually the mechanism. This is alpha cleavage of 3-pentanone for 29 peak. How 29 peak appear? So this is 29 peak. Now positive charge remain here, radical remains on the carbon. Okay. This is one more example of halogen. We'll skip this because multiple examples we have taken. We have limited time also. Just 5 minutes are remaining. So we'll clear this multiple bond. Yes, we come on that. Multiple bond cleavage. Multiple bond cleavage means in fragmentation, suppose more than one bond get cleaved. This is called as multiple bond cleavage. This is the last part from fragmentation patterns or the mechanisms. Okay, sigma cleavage, alpha cleavage, then inductive cleavage, and fourth one is multiple bond cleavage. Generally, in McLafferty rearrangement, you may observe this multiple bond cleavage. More than one bond is get opened. So if your structure is a ring structure, ring can be opened. If your structure is a chain structure, then it may give out a neutral compound. It may give out a neutral compound. Like this is the compound CHCZ. Okay, CHCZ. This is the compound. And when multiple bonds get open, the C double bond C will form here. This is positive with a radical, and HZ will be eliminated. This hydrogen is migrated towards Z. This is a heteroatom. It may be a chlorine, so that will be HCl. It may be bromine, that may be HBr. If it is NH2, that will be ammonia, likewise. So HZ will be eliminated as a neutral molecule. So in that, multiple bonds are broken. CH bond is broken, CZ bond is broken. And that's why this is called as multiple bond cleavage. This is a retroaldehyde Diels-Alder reaction. In retro-Diels-Alder reaction, you can see multiple bond break here, and this ring get open, and it eliminate the ethylene ion, ethylene molecule. It eliminate the ethylene molecule and give out the radical ion together. Okay, so these are some examples of multiple bond cleavage. Of course, one of the multiple bond cleavage is McLafferty rearrangement. We have one more example of that. This is cyclic compound, how the cycle get open and how the multiple bond cleavage takes place step by step. Okay, so that is explained herein. This is McLafferty rearrangement, full mechanism and abbreviated. You can show this like abbreviated mechanism here. Double bond, carbon and oxygen may be present here. CO double bond is present, and this is gamma hydrogen. Gamma hydrogen is generally required for McLafferty rearrangement. This hydrogen get migrated on the oxygen. That will become an OH plus. Okay, and if it is nitrogen, then that may be NH2 plus, etc. Always McLafferty rearrangement eliminate one neutral molecule. This is one of the example of 3-methyl-2-pentanone. Okay, alpha, beta, gamma. So here is the gamma hydrogen. Gamma hydrogen can be moved towards oxygen, and it give out one. This ethylene group can be eliminated, and this radical may be formed. This sorry, not radical. This is ion. This ion will be formed CH3CO CH3. Okay. Now in this, you can see 100, 72, 57, 43, and 29 are the major peaks. These are major peaks. Now we'll see one by one how fragmentation takes place. Okay, this is the fragmentation. This is 100 means a molecular ion peak. It is fragmented into this peak. This is 43. Okay, then this is one of the rearrangement that positive charge migrated towards carbon. This is carbocation now. This carbocation shows inductive cleavage. It shows inductive cleavage, and it gives this ion. The mass is 57. Then this carbocation gives inductive cleavage from beta bond, not from alpha bond, but from beta bond, and it gives you, yeah, and this gives you one more mass here, 29. So you have 29, 57, and 43 mass. See here, 29, 57 and 43 mass. Okay, but what is 72? 72 is not explained in this. 100 is the molecular mass. 72 is not explained in this. What is 72? This 72 is McLafferty rearrangement. Okay, this is McLafferty rearrangement. You can see here, hydrogen first migrated on oxygen. This is OH plus because oxygen has trivalency here. So OH plus. And now this radical form a double bond with a neighboring carbon, and that will split a beta bond here. So this is elimination of ethylene neutral molecule with this fragment, and the mass of this fragment is 72. Okay, otherwise by splitting you can see 71 actually, but this is 72. Now come to the mass spectrum again. 100, a even number. 100 is even number. It gives you a fragment 72 again even. Is it possible that 100 even can give you even fragment? Theoretically, it should not give. But because of McLafferty rearrangement, one hydrogen is shifted on the ion, and that's why the mass is increased by 1. Otherwise, the mass of that ion is 71. And even mass can give you odd fragment. Okay, so that fragmentation is possible, but due to McLafferty rearrangement, the mass of the ion will increase by 1, and that appear at 72. So in this, we can see that this 100 may be a wrong molecular mass, but that is not wrong. Okay, so here McLafferty rearrangement takes place. That's why even gives you even fragment. Okay. So here these are without McLafferty rearrangement. You can see here 100 gives 57. That is even to odd. 100 gives you 43, again even to odd, and 100 gives you 29, again even to odd. Only in McLafferty rearrangement, this law doesn't help. That even gives you even. Okay, so this is what fragmentation is, and such knowledge is required prior to interpret the mass spectrum. And now if the mass spectrum is given to you, by applying your knowledge regarding this cleavage and all this, you can try to interpret the exact structure of the molecule. Okay, now these are some approach to analyzing spectrum. How to interpret the spectrum? Some approaches are given here. First of all, squeeze out everything you can out from the mass spectrum. Okay, M plus peak is there, molecular ion peak is there. Now, how the peak is, what is the intensity of the peak, what is the value of the peak, which is the next fragment of the peak, whatever the data you can squeeze out it. Then, which are the point for that? My molecular ion peak, whether the molecular ion peak is stronger or weaker, whether the isotopes are present or not, like M plus 1, M plus 2, M plus 4, likewise. Okay, whether the C13 present or not, whether or how many carbons are C13 there. So apply for the nitrogen rule, apply for the rule 13 if possible, then find out the presence and characteristic peak like M minus 1, M minus 18. M minus 18 shows alcohol presence, M minus 1 shows the aldehydic presence. Okay, so later way. Then second, squeeze out everything you can out from the base peak. Base peak is the tallest peak. Okay, what ion could give this base peak? Then what was lost from the molecular ion to give this base peak? So that radical. And then when considering the base peak, initially only think on the most common cleavage like sigma cleavage, alpha cleavage, inductive cleavage. First think about most common cleavage to find out what is eliminated. Okay, McLafferty rearrangement is not a common. Then third point, look for the masses of a small neutral molecule from molecular ion. These masses may be get eliminated from the molecular ion. So look out for these possible masses to get eliminated from the molecular ion. Then now consider the possible diagnostic peaks. These are few diagnostic peaks. Diagnostic peaks generally gives you idea about what is present. See 105, 91, 77. 77 is phenyl ring. 91 is benzyl ring. 105 is para carbonyl benzene ring. Okay, benzene ring with one carbonyl group at the alpha position. Okay, then 31 is methoxy group. Okay, 29 is ethyl group, right? Similarly, 45, 31, 45 and 59 are alcohol, primary alcohol, secondary alcohol and tertiary alcohols. Okay, so these are called as diagnostic peak. find out whether these peaks are possible and these peaks are observed on the spectrum or not. And lastly, once you have hypothetical molecule with you, then just to confirm, just to verify it, use the other less intense peak from the spectrum. So there we have to go on the smaller peaks. Otherwise, smaller peaks are never interpreted initially. Okay. So this is, I think, enough for mass spectrometric analysis and interpretation. These are some peaks, and these are given in the literature also. No need. These are given in the literature. Which type of chemical and which type of functional group shows you which abundant peaks. Okay. These are most abundant peaks and very, very characteristic peak, like aromatic 77, 91, 105. Okay. Just before I told you about halides, see, M-79, M-81 is definitely bromine. M-36, M-38 is definitely HCl. Okay, chlorine with one hydrogen. Okay. Similarly, if alcohol is there, M-18 is a characteristic peak. Likewise, 31 is for primary alcohol, 45 for secondary alcohol, 59 for tertiary alcohol. Okay. Then phenol, M-1. And also M-1 is reported in aldehydes also. See, aldehyde, M-1. Where is this? Is M-1. Aromatic aldehydes, loss of one hydrogen. Okay. Similarly, there are so many characteristic peak, and all this table indicate the characteristic peak, which shows you generally what may be present in the molecule. These are also called as diagnostic peak. So we can diagnose the molecular mass, we can diagnose the functional group present in the compound. Okay. And this is one of the problem which we have shown, but I don't know, sir. May I have some time?
Sir, actually, next speaker has also joined.
Okay. Okay. So, sir, we will stop here only.
Yes, sir. Yes, sir. Okay. Thank you, sir.
Okay. Okay. Thank you.
Yes, Gondari, sir. Gondari, sir.
Yes, sir.
Yes.
Yes. Sorry, sir.
Yes, sir. Dear audience, this is the session open for question answers. If you have any doubts, you can ask. Okay, with no doubts, Gunjari sir, can you share the slides, please?
Yes, sir.
Devaki. Miss Lava.
There is a technical issue. Please hold on.
Yes, Savi, sir.
Yeah. So with the time limit, sir has stopped the problem solving. So actually, sir has very nicely explaining the interpretation of the mass spectrum. So sir has started with ionization and fragmentation, and also sir has explained about the nitrogen rule and rule 13. And sir has also explained about the cleavage, types of the cleavage, that is the homolytic cleavage and heterolytic cleavage and multiple bond cleavage. Sir has taken very well about the different examples of the spectrum of the different compounds. So with this, I express my sincere thanks on behalf of Government College of Pharmacy to Kondawar sir for giving his valuable time with us and sharing his knowledge to our participant. And with this, I'm very much thankful you, sir.
Thank
And
you,
now I
sir.
request to Gondari, sir, to present a certificate of appreciation to the Kondawar, sir.
Thank you, sir. Thank you.
Thank you very much, sir.
Sir, thank you very much.
Thank you, sir.
Okay, see you, sir. Okay. Now, probably next speaker has joined. So, Gonzalez sir, we will start with the introduction.
Yeah.
Anil sir, are you there?
Yes, sir. I'm.
Yes.
Yeah,
Shall
we
we
are.
start? Shall we start?
Yeah, once again, welcome to all the participants and our speaker for the fourth session, Dr. Anil Kumar and Dr. Chandrasekhar N. Dr. Umbarkar,
Yes, sir.
yeah, you can please take over the session.
Sir, we are having two sessions now. So first will be of Dr. Chandrasekhar N. Isn't it?
Yes, sir.
Yes, sir.
Yeah. Okay. Yes.
We have two sessions of 45 minutes each.
Yeah. Okay. A very good afternoon to all. I welcome you all to today's last session. And for this, we have with us a very dynamic personality, Dr. Chandrasekhar N, who will guide us on introduction to NMR spectroscopy and its applications. I kindly request our respected principal, Dr. K.B. Burade, sir, to felicitate our guest speaker with the e-bouquet.
Thank you, sir.
Yeah, kindly accept the welcome, sir. Now it's my immense pleasure to introduce our guest speaker, Dr. Chandrasekhar N. He's after completion of his MSc in inorganic chemistry in 1998 from Central College, Bangalore University. Bangalore. Yes. Worked short period in NMR Research Center, IISc Bangalore, and joined Brooker India Scientific Private Limited, Bangalore in 2000 as an application scientist. He did NMR service and application support to all academics, industry, and pharma customers of entire India. He received his PhD degree in inorganic chemistry from Central College, Bangalore University, Bangalore, under the guidance of Professor N.M. Nanje Gowda sir, and under the co-guidance of Professor K.V. Ramanathan sir, NMR Research Center, IISc Bangalore, for NMR studies. So with this brief introduction, I request Dr. Chandrasekhar N to kindly proceed for the session. Over to Chandrasekhar sir.
You are now host, Chandrasekhar sir. So you can share the screen. Hello.
Yeah, just a minute, sir. He has some
Hi.
technical issue. He is
Yes,
just
yes.
joining.
No problem. Your voice is not clear.
Hello.
Now it's clear.
Okay. Now? Okay. So I'll share my screen.
Yes.
Yes, sir. Host is disabled participant screen share. You have to allow us to share.
Yes.
Now, host is disabled participant screen sharing. It comes.
Yes, don't do it now. Now you are co-host.
can see my screen?
Yes, yes. You can proceed, sir, now.
Yeah. Yeah, good afternoon. So, welcome from my side. So, today I'm going to present on introduction to NMR spectroscopy. So, this is the agenda of my topic. So, initially I'm going to cover a little bit of history, and then the next I will go to the next basics of NMR. So, what are the basic principles?
Sir, you are not audible.
Hello.
Your voice is a little bit low.
Hello. Okay.
Actually,
Hello. Now
it's echo like sound, sir.
Coming like
because of
echo.
that.
Yeah.
Because usually we
If you logged with the two device, no, for one you know the volume of one device.
okay. Should I? No, I have only one is the.
Now it is audible, sir. You can proceed.
Oh. Okay. So next I'm going to cover about these factors, the NMR signals, and then some of the spectral information. And at the end, I will cover the NMR applications, the wide range of NMR applications I'm going to cover. So if you look at the history of the NMR, first most of the talks, they start with the Nobel Prize winners in that particular field. So if you take the NMR field, there are a lot of Nobel Prize winners are there. So normally what we start with is, in this with Felix Bloch and then Edward Purcell, who shared the Nobel Prize in 1952 for physics. So both they work independently. They discovered this NMR, and they get the detection of the NMR in the bulk matter. And NMR became more popular in the late 90s when Richard Ernst he got the Nobel Prize in chemistry in 1991 for his work on this pulsed technique and then Fourier transformation methods. And later from the same university, like ETH Zurich, and in the 2002, Kurt Uttridge, he got the Nobel Prize in chemistry for developing a three-dimensional methods, 3D techniques for protein structure analysis. And in the field of medicine also, later in 2003, the Peter Lauterbur and then Mansfield, they both shared the Nobel Prize in chemistry for discovering the MRI, magnetic resonance imaging. So these are there are some indirect Nobel Prizes also is there. For example, if you take the superconductivity, there are also this nowadays we have used regularly the superconducting magnets. So these are the major main Nobel Prize winners, what we see. So if you look at the contributions from Indian scientists in the field of NMR, first comes is Professor G. Suryan, which Professor in IISc. He worked on NMR in the flowing liquids and then radiation damping. And from the TAFR, that Mumbai, it's SS Dharmati. So who is discovered this chemical shift, this one, and then Professor C.L. Ketrapal from IISc Bangalore again. He worked extensively on this oriented molecules. The major contribution comes from Professor Anil Kumar. He is faculty in IISc, in the retired faculty, and who worked extensively on this two-dimensional NMR, NOG, and Fourier transformation. So he worked with the two Nobel laureates, like what we said in the Richard Ernst, and he worked in 2 years there. And then in the later stage, he worked with the Kurt Uttridge for the NOG experimental, for the NOG experiments. And his contribution is recognized in both the Nobel Prize winners. So if you look at that, some of the early NMR spectrometers, they are very highly bulky. So if you look at this magnet and probe assembly, which is delivered with the first NMR system, 25 megahertz per minute magnet instrument.
Sir, you are not audible. Again, the voice is very low. Not.
Hello.
Actually, my problem is there. or network issue might be the problem.
I am
Anil sir,
in some remote location.
Yeah, that is the problem.
Hello.
Actually, we are not getting any voice from your side.
Wow.
You keep mic.
Hello.
Hello. Probably internet issue is there, right? Means your voice is not clear. You cannot understand the things. What I thought, if we start first with the Anil sir, and then after that, if you take your lecture.
Yeah, I'm in the remote location at customer place.
Anil sir.
Yes, sir.
From
I
the
didn't get what is the problem from Chandrasekhar side.
Yeah. You are able to hear me?
Yeah, you are.
Hello.
You are very clear, sir.
Okay.
But from sir, we are not getting voice.
Okay, maybe he will try to adjust that. Meanwhile, I can start mine.
Yes, sir. Yes, sir. Yes, sir.
Okay, I'm sharing my screen. You're able to see my screen, sir?
Yes, sir.
Okay, sorry for that problem.
No problem.
Yeah, so once again, welcome everyone from my side. So I'm Dr. Anil Kumar from Brooker India. Mainly, I'm responsible for sales. Although I started as an application scientist, I moved into sales and looking after West and South India. So I will start directly with the Brooker history. My topic today is more on Brooker NMR with respect to hardware and software. However, I'll give a kind of a brief about the Brooker history. So Brooker has more than 60 years of innovation, where the foundation stone was first laid by Professor Gunther Laukin, who was our the startup company, which was started way back in 1960, along with Professor Brooker. And in the beginning, it was only limited to NMR. However, as we moved up, we moved not only into NMR, but also into mass spectrometry, X-ray, optical spectroscopy, etc. And now we are the number one company in NMR field. Basically, if you look at Brooker, it's mainly a magnetic resonance at the heart of the company. So where we are investing nearly 10% of our profits in mainly research and development. Because of this kind of investment, we are getting a cutting edge innovation like a gigahertz NMR or DNP, DNP NMR, etc. And we are not only limited to only NMR, we are also into EPR, which is electron paramagnetic resonance, and also MRI magnetic resonance system, which is mainly in preclinical. So if you look at some of the highly applied markets, we are also into NMR food screener or in vitro diagnostics, mainly for metabolomic kind of studies. And we also have a few benchtop NMR system. So these were kind of respect to the hardware. But if you look at the software, once again, Brooker is concentrating on many software solutions like complete molecular confidence suite, smart drive, and TopSpin is the main processing software and also acquisition software which Brooker is heavily investing. In terms of pharma, we are also coming up with new technologies like a fragment-based drug design. The potency MR is nothing but trying to find the potency or the impurity kind of profiling. The insight MR is mainly the reaction kinetics. So these are the kind of pharma investment which we are doing. And in addition to that, we are also heavily investing in service and aftermarket support, which is our LabScape portfolio. If you look at the application support, what we have is a demo lab in Fellenden, which is based close to Zurich, It was opened in July 2016, mainly to cater our global customers. We have one more demo center in Germany, Ettlingen. So this was only opened last year, and it offers the modern and personalized kind of experience, mainly trying to cater all the new customer applications globally. If you look at the scientific markets, Bruker is having a wide portfolio where we have more than 70% of our portfolio, um, and it is holding either number one or number two kind of market position. So these are the kind of system where Bruker is heavily investing in NMR, mass spectrometer, AFM, X-ray, NIR, etc. When you come to Bruker Corporation, we have 4 different divisions, and I am representing the Bruker Biospin Group, which mainly deals with magnetic resonance spectroscopy and preclinical imaging or applied industrial and clinical. You might have heard in the last 2-3 days, or maybe you might hear something from my colleagues also from other divisions, mainly like a Khalid group, which is dealing with mass spectrometer and infrared and Raman spectroscopy, also the detection. The Bruker Nano group is mainly into X-ray, nanosurface, etc. And we have the Bruker, our own research and development division, mainly for developing the superconducting wires, which is used in our magnets. So this is called the BEST division. In the Bruker Biospin, we have further 4 divisions, which is magnetic resonance spectroscopy, where we try to cater academia, government, and educational institutes, and also the pharma and industries. We have a separate division for applied industrial and clinical, mainly catering the food, feed, and beverage, and also into clinical research. The PCI division, which is a preclinical imaging, is mainly concentrating on applied research and fundamental research. All these are catered by our service and lifecycle support, which is our service division, mainly doing the services, training, support and maintenance, and also they are into upgrades or consumables and accessories. So when you say about NMR, I'm sorry that my colleague Dr. Chandrasekhar couldn't present, but this is how you see the NMR. Basically, it's 1 second. I'll just open the pointer. So what you have is basically a magnet. This is a superconducting magnet. The second important is the console, which is the electronics which is holding, and then there is a probe which is inserted into the magnet. So this is the main heart of the NMR. So these are the 3 components: the magnet, the console, and the probe. So depending on the console electronics, you can do either liquid state, the solid state, or even the imaging. So it depends on the probe as well. So which we'll see in the later slides. So coming to Bruker India, we have more than 80% NMR market share, where we have more than 489 systems with 21 people supporting all our customers. So we have around 13 service people and 3 application scientists, and there are 7 people who are also involved in sales and application service. We have over 8 branches in India, and in West region itself, we have more than 100 NMRs, and South region, we have more than 200 NMRs. The highest installed NMR in India is 800 megahertz, so which are installed at 4 different places. Because it's a heavily kind of priced, people are thinking of going for the higher megahertz. So the first one is in TFR Mumbai, then there is a CBMR Lucknow, and then IAC Bangalore and NCBS Bangalore. So this is 800 megahertz is installed in 4 different places in India. So now I come to the first part, which is the magnet. So as you know, the magnets are superconducting magnet, and Bruker is developing our own magnets for the last more than 4 decades. So because of the development in technology in superconducting wires, like maybe you might have read already, the 400 megahertz is using a different kind of alloy rather than when you go for a 500. And when you move from 500 to 700, once again, the alloy changes. So this is because of the kind of electricity which you pass through into the superconducting wires, which has to withhold such type of high currents. So the recent magnet which is installed is the Ascent type of magnet. And when you look at the portfolio, we have a wide range. So as you can see here, so the Ascent magnet, it starts from 300 megahertz and it can go up to 1200 megahertz. So that is 1.2 gigahertz. So this is for mainly catering kind of a liquid state mainly. If you are looking at solid state, then it starts from 300 megahertz up to 900 megahertz. So this is a kind of wide portfolio we have in terms of magnets. And the second part is the Avance Neo console. So the Avance Neo console is once again the electronics. So you might have heard already or read the NMR. If you want to study your NMR sample, you have to dissolve your samples into a kind of organic solvents like chloroform or dichloromethane or THF, DMSO, such kind. And if your sample is soluble, then you will go for a dedicated kind of liquid state. If it's a dedicated liquid state type of NMR, then you go for a nanobay, which is a 2-channel system. So 2 channels in the sense, like the first channel is the proton and the second channel will be the X nuclei. X means you can do either carbon, nitrogen, phosphorus, any nuclei which falls within a certain range. So this is the nanobay. And in case you want to study other than liquid state, if you want to study also solid state sample, then the electronics will change, because for solid state, you need a higher power amplifiers and other accessories as well. And in case you want to do like a 3-channel kind of experiments, like if you want to study proteins and peptides, like 3-dimensional NMR, then you need to go for a 3-channel. So then you need to go for a 1-bay. And in case you are also interested for higher kind of specialized experiments, which involves 4-channel or above, or you have some special applications like imaging and all, then you need to go for a double-bay. So these are the 3 different kind of variants we have in Avance Neo consoles. And depending on the application and depending on your sample of study, you have to go for different type of consoles. So when I say the Avance Neo, so this has a very long history. The first generation of Avance series came way back nearly 2 decades ago, way back in 2000, where we had our first Avance series. And because of certain development, we went for future improvements, like we came up with Avance 2, Avance 3, Avance 3 HD. And since 2017, we have the Avance Neo. So what is the reason for going for a different kind of generation of electronics? This is, as I said, there is a certain improvement, like people wanted to go for higher speed, or they wanted to have better resolution and better sensitivity, or maybe they wanted a kind of higher throughput, or even the sample purity. So because of all these advancements in either the NMR sample or the electronics, Bruker could come up with the various generation. And Avance Neo is a recent well-established kind of electronics we have, and it's the state of art. So why do you need NMR? Like the top 5 reasons for Avance Neo. If you have already done some NMR in the earlier years, so you would know that you would in the earlier years you could do only one experiment at a single time. Like you could do only proton NMR, and after that, for the same sample, you could do carbon NMR. However, with Avance Neo, you have a multi-receiver kind of technology. That means you can, depending on the number of receivers you have, you can be able to run 2 or 3 experiments simultaneously. So in terms of industry standard, like time is money. Like if you save time, you save money as well. Yeah, for example, just to give, let us say you have a sample which takes maybe 3 hours to run a simple carbon NMR. So if The 3 hours in the earlier years would be wasted on one single experiment. But if you have a multi-receiver, you will be able to do, depending on your channels, you will be able to do either 2 experiments or 3 experiments simultaneously. That means in 3 hours, you would have 2 experiments already acquired, and you already have the process data. So this is the kind of advantage you have. The second advantage is the enhanced dynamic range, which effectively means not all chemists or any spectroscopists will have a high quantity of samples. So that effectively means you are either, if you have a sample quantity of low concentration, then you need to run for more number of scans. However, with Avance Neo, since it has an enhanced dynamic range, so that effectively means even with less number of scans, you'll be able to get good signal. So this is the kind of advantage you have. The third one is the speed. So this is the simultaneous event time. So once again, as the electronic speed is improved, you'll be able to better acquire. So whatever samples you could, for one experiment, it might have taken in the earlier years, maybe 1 hour or 2 hours, or even 10 minutes. So such kind of experiments with Avance Neo, you'll be able to run within a few minutes, like 1 or 2 minutes or something, or whichever was in hours, you can reduce to a few minutes. So this is the speed. The fourth one is that it's designed for future. That means the same kind of architecture is there from 300 megahertz up to 1.2 gigahertz. The fourth one is mainly for the operating system. So why this becomes more important, mainly I want to point in pharmacy, because you are from a government pharmacy college. You will see a lot of students who work in pharma. They are exposed to the kind of good laboratory practices and GXP environment, where there is a lot of compliance audit, which is done by US FDA or European FDA. So if that is the case in many of the pharma industry, so then you need to have a kind of a data integrity, which is very crucial. So for catering that need, we have an operating system which is independent of console operating system. So to protect the data integrity. So as I said, I already mentioned in Avance Neo, you can run 2 or more kind of experiments. Just to give a small example, if let's say you have a Avance Neo Nano Bay, so that means you have a 2 channel. So that effectively means you have 2 receivers. What it means is like you can do a 1D proton and fluorine simultaneously, or proton and boron simultaneously. So earlier years you could only do proton. After finishing the proton, you could do fluorine or boron. So in this kind of multi-receiver, you will be able to run both simultaneously. This is not restricted only to 1D. If you go for 2D, then once again, you can do HF correlation or HH correlation, all cozy interactions, or FF correlation or fluorine proton correlation. So this is also possible. And if you go to diffusion experiments, you can run proton and fluorine diffusion experiments simultaneously. So then you have a cozy het core. So that means you can do a proton-proton correlation and proton-carbon correlation. If you have run already a NMR in the earlier years, a cozy usually used to take at least 2 to 3 hours, and het core would have taken another 2-3 hours. So with the multi-receiver, within the 2-3 hours, you will have both the experiments already done. So Toxi and het core. So there are so many experiments, and if you have a 3-channel with 3 receivers, then it's even more. You can do even more experiments. So within the simultaneous time. And then what else do you gain? You with the generation of this dynamic range, you will have a 20 to 30% higher sensitivity. And I already mentioned about multi-receive capability. If you have automation, like if you have a auto sampler or something, then you will have a stable and kind of reproducible NMR data. And it's a kind of state of art electronics, because all experiments which are even published very recently in the last year or so, all these are already integrated into our top spin software, and it's ready for even future developments. So these are the kind of advantages you have. Just to give a few example, and anything I say without the data doesn't look good. So this is a kind of one kind of the first of the data which I'm showing. So let's assume you have a 3-channel instrument. So that means here what you see the data is a proton carbon and a proton proton and proton nitrogen kind of experiments which is already done. So this is a 3-channel, and this is done within a few minutes, and that was a liquid state. So in case you have a solid state probe also and solid state electronics, then once again you can do the multi-receiver kind of electronics. You will be able to run proton carbon head core, that is a proton carbon correlation and proton nitrogen correlation. So both are done simultaneously and within a few minutes. And more example, like this is a kind of a toxi, and then there is a proton carbon head core, all done within 4 minutes, within 4 scans, and within 40 minutes. And more examples is HSQC and COSY. So where there are you could run HSQC and proton correlation and carbon proton correlation. All these experiments, however, since I am showing already, in fact, would have been introduced to you by Dr. Chandrasekhar, but there, because of technical problem, he will be explaining these experiments in the next few minutes. So these are the experiments which are all possible within a single experiment, and this is a super sequence you can run within few minutes. Like in this example, it's a pomoic acid, 50 millimolar, and within 30 minutes, you are able to get the HSQC and 2 different type of COSIs already in this. And more example, like in this experiment, it's HSQC, HMBC, COSI, and NOSI, all done within within few minutes. The other advantage we saw in Avance Neo was during the pandemic when Corona started. So people were actually working from home. So that means many of the industries had this issue that maybe there might be a power problem or something. Then they had to shut down their instrument, and they couldn't go to the industry. So we have this where you can log in directly from your home and enter into your spectrometer PC. There you could switch on or switch off or even reboot. So this was also possible. 1 second. Excuse me. So I mentioned about enhanced dynamic range. So that means in the earlier years or earlier spectrometer, even with receiver gain of 4, your signal was lost in the noise itself. However, with Avance Neo, you will be able to see even a smaller signal apart from your noise region. That means you will be able to recognize even small impurities which come in a lower concentration. So this is the advantage of going for enhanced dynamic range. And if you have a solid state sample, then this is the mass unit which you will be using for mainly spinning your sample or to remove your sample up and down, like to insert your sample or eject your sample. So this is the kind of hardware unit which is dedicated for solid state NMR. So that was about the magnet and the electronics. Now coming to the third part, which is the probe. So this is a kind of a cross section of a magnet. So what you see here is this is the superconducting wire. What you see here. So basically, what happens is there is a upper like a shim turbine and a lower shim turbine, and the probe will go inside this and sit perfectly in the middle of this superconducting or the magnetic field. So the principle will be explained anyway by Dr. Chandrasekhar. So what happens is basically in the probe, you are exciting the nuclear spins and then you are detecting the NMR signal. So what the probe does is, so the probe, as I said, it goes inside the magnet, and whereby it tries to align in such a way that the RF coil sits right in the middle of this superconducting wire. So thereby it is at the center of the magnetic field. So the probe also contains the RF coils which are inbuilt, which you see here. I will show in another slide how the RF coil looks like. And this is basically where you tune to either a proton or X channel. Like X channel can be, as I said, it can be carbon, nitrogen, or something. So there you are trying to tune to that specific frequency in the magnetic field. And then probe also needs the kind of hardware to control the sample temperature or something. So where does the sample comes from? You are inserting the sample from above and it goes directly and sits in the magnetic field. So there you have the spinner where that means you have the sample tube which is inserted into the spinner, and there is your sample which is exactly in the middle of your RF coil as well as your magnetic field. So this is how probe and magnet looks like. And when it comes to the probe also all are manufactured by Bruker. However, when you choose the probe, as I said, depending on your sample, you have to choose which kind of probes you need to go for. Like if your samples are soluble in any organic solvents, then you can go for solution state probe. If it's a kind of non-soluble, then you go for a solid state probe. And then if it's a kind of in between, like a semi-solid, if it's a gel-like sample or a thin film kind of thing, then you have another probe for running the semi-solid kind of states. So depending on the kind of probes, you have to choose the applications as well. So and they also come in different variants, like it can be selective nucleus. Say for example, you are interested only in proton, you don't need any other nuclei, then we have that kind of probe. Or if you are interested in proton and carbon, then we have a dual probe. If you are doing a kind of peptide kind of samples where it's usually proton, carbon, and nitrogen, then we have triple resonance. However, what we see is a majority, more than 90% of our customers, they go for broadband. That means it's usually a 2-channel where they have a proton, and the second channel is the second channel is the carbon or kind of broadband where you can run different kind of nuclei. So then you have the solid state probe, and you have the micro probes or cryo probes as well. So coming to the probes, there are different kind of liquid state probes. The first probe is RT liquid state probe, where you have a kind of room temperature coils, which is around 292 to 300 degree Kelvin, depending on the air what you are passing through. However, we also have some specialized probe where the coil temperature can be cooled down to nitrogen. So where this is the help of this is sensitivity enhancement, where in principle you get nearly twice the sensitivity when compared to the room temperature probe. We also have a kind of another advancement, which is the helium cooled cryo probe. Then it's the coil temperature will be around 15 to 25 Kelvin, where you get a sensitivity of nearly 4 times that of the room temperature probe. So this is the kind of advantage you go for. However, the prices also kind of increase. So when I already mentioned about RF coils. So this is the kind of RF coil what you see here, the kind of copper color, and the brown color what you see is the sample which is going and sitting inside that RF coil. So if the inner, there are 2 type of coils here, saddle coils. So if the inner coil is like a proton, then you have a inverse probe. And if the outer coil is a proton, then it is called a observed probe. So these are the 2 different kind of variants you have. And I'm going to explain more on the room temperature probes. So the Bruker I probe is the latest generation. And depending on your sample, you have to go for either a high resolution or a solid state or a semi-solid kind of sample. The advantage, all these 3 probes might look similar. However, they are different for different samples. So if you go for liquid state, it's a different probe. If you go for a solid state, it's a different probe. So the main advantage is, unlike in the earlier years, where you had to go below the magnet and you have to tune and match for different frequencies. Now they are all automated, and you can do everything via the software itself. So even the adjustment of magical angle or insertion and ejection of your sample, all are possible using the software. So the advantages are there is a proton sensitivity, which is improved, the external, which is improved also when compared to the earlier generation. And because of the time, I might go in a faster way. Excuse me for that. So we also see there are a lot of new applications now where pharma industries and pharma colleges are more interested in fluorine NMR. So if you run this is a trifluorotoluene, when you run a fluorine, you might see a kind of broad signal. However, when you decouple it, you get a better sensitivity. So similarly for other samples as well. So you see the signal to noise ratio, because of the decoupling, you are getting a higher signal to noise ratio. And I already mentioned about multi-receiver kind of technology, and where here this is a cyclosporine, where HSQC, a COSY proton-proton correlation, NOSY, which is a proton-proton correlation over space. These are all done within 26 minutes. So this is the kind of advantage you get. So it's our probes are not only limited to the normal nuclei. You can also run some special nuclei. Like here, there is a 207 lead, which you can run at different kind of temperatures. As you can see, as you move the temperature, as you heat it up, the chemical shift is increasing. So this is the kind of study you can do using NMR as well. It's not only limited to proton, fluorine, or phosphorus. You can do even boron or even platinum, say for example. And in terms of solid state, once again, depending on the temperature and the sample kind of studies, there are different kind of probes which are available. Usually it is the VTN probe, which has a kind of minus 120 to plus 120 or 140 kind of temperature range. However, there are different kind of probes depending on your sample and the research what you are planning for. So how does a sample for solid state holder looks like? These are the kind of sample holders for inserting the solid state sample. They come in various sizes. It starts from 7 mm and it can go down to 0.7 mm. So you can see how the smallest 0.7 mm probe, when you compare to the matchstick, this is even kind of very small. So it's not really visible to the human eye. So you have to, when you insert your samples into this, then you need to use a microscope. And the main advantage here is, as you go down, you get a better sensitivity and a better resolution. And also, because of the different diameters, you can spin at various speeds. So for 7 mm, it's 7 kilohertz. And for 0.7 mm, it's 111 kilohertz. So this is the kind of advantage. And I already mentioned about the HR mass probe, which is for semi-solids. So here, what you do is basically you insert into a kind of disposable insert the semi-liquid or gel sample, and then you insert into the rotor and then you spin it. So this kind of probes are available from 400 up to 600 megahertz, and these have all the advantages what you just saw before in the eye probes. So I mentioned now all the hardware, and the last one is the automation. So as you know, you might have a higher throughput, so you need to use sometimes the auto sampler. So the variants we have is either a 24 sample or a 60 sample. So it is maintained at user height, and these are the different samples which are loaded, and it's easy to operate, and even it can be controlled by our software. So when I mention software, the software what we have is a TopSpin 4 for doing both the acquisition as well as the processing. So the TopSpin 4 is a kind of a new and intuitive. It's a very user friendly, and it's having all the processing capability even with older formats. So the main advantage here is it has a kind of library where you just by choosing what kind of experiments you would like to do, you click on here, like if you want to do a 1D or a 2D, or if you want to do multi-receiver experiments, all these can be chosen directly over here, and they are also kind of customizable because of the library which is already inbuilt. we have a wide portfolio of different softwares for different kind of analysis. Like if you want to study structure, then that is possible. If you want to do concentration or the quality of the sample, we have another software. If you want to do find the purity, it's possible. You can even calibrate your instrument using the auto calibrate. So such kind of all different kind of software portfolio also we have. And because of the time limitation, I will end my talk and I will pass on to Dr. Chandrasekhar.
Yes, Umbarkar sir.
Thank you, sir. So due to some technical issues, Chandrasekhar sir could not present. Now he will continue the session. So I left the introduction of Dr. Anil Kumar sir. So let me introduce sir with a brief information. Dr. Anil Kumar sir is a senior sales manager and application scientist at Brooker India Scientific Private Limited. And he received his PhD in inorganic chemistry from ETH Zurich, Switzerland in 2005, and then held a postdoc position at the University of Western Sydney in Australia. Dr. Anil joined the applications team at Brooker India, Mumbai in 2007 and did NMR service and application support to all the academics, industry, and pharma customers in his region. So we have with us the most eminent and great personality. He has given a very nice and informative session for our participants. I thank Dr. Anil Kumar sir, and I would like to request Dr. Gonzari sir to present a certificate of appreciation for the Dr. Anil Kumar sir. Dr. Gonzari sir.
Sir, can I make a request here? Dr. Chandrasekhar is online, and if possible, he will try to continue his presentation as well.
Yes, we'll finish first presentation.
Yes, sir.
And then we'll go for thanks.
Sure, sir. Sure, sir.
Yes, sir.
Yes,
Yeah.
Umbarkar sir.
हाँ, sir. Yes.
Continue करायला सांगा sir.
Okay. So now we will have a session of Dr. Chandrasekhar and sir. So over to Dr. Chandrasekhar.
Hello.
Yeah.
Yes, sir.
This is the most disabled participant screen share. Can I have it now?
Yeah, yes.
Yes, you are now co-host, sir.
Okay. You are able to see my screen?
Yes, sir.
Yes, sir. Yes.
Yes.
Okay. So sorry for the technical problem. I am in remote location actually in the customer place. So here the network is very poor. I tried with some other device. So let me see, how much time I can try to make it. So here, so earlier, I was showing some of our old spectrometer. So how it looks, and this is the present spectrometer, recently installed 400 megahertz system. So as my colleague explained very detailed. So this is our electronic spot where you can see this, advanced Neo system, and this is the magnetic port, and this is the auto sampler, where we can put all your samples in the series, and then you can set up the experiments. And here we have a computer to control the system. So this is our present NMR system, very small in nature. I mean, even if compared to the very earlier old systems, but magnetic part is still bigger. Okay, so now let me start with a short introduction of the NMR. So as the name suggests, it's a nuclear magnetic resonance, which is an analytical technique. So this tool is mainly used to determine the structure of all kind of molecules like organic molecule or inorganic or biological, any kind of molecules. And also apart from that, you can have a lot of applications in other area like material science, medicine or geology and so many things. So as the name, nuclei implies that we look at the nuclei and their magnetic moments. And the magnetic part implies that there must be a magnetic field in one. And resonance, which gives you the impression that there must be some oscillatory magnetic field and whose frequencies will match. And what we say in the terms of NMR is they resonate each other. So when you put a sample inside the magnetic field, strong magnetic field, so that some electronic structure of the molecules, so they get changed, they get deformed or changed. So these changes, they induce a tiny magnetic field. So which can be either they lie along with the magnetic field, that means applied magnetic. They can either oppose or they can reinforce along with the magnetic field. So these reduced magnetic fields, if we back calculate, then we can define the structure of any molecule. So here. So if you look at some of the examples, how the molecule will behave in presence of the magnetic field. So let us take a benzene molecule. So benzene molecules, the protons which are outside the ring, so these nuclei, so they reinforces along with the applied magnetic field. That's why what we say in the NMR terminology is they are de-shielded. They comes at the high frequency or low magnetic field. And the some of the signals which are live within the ring, they opposes the applied magnetic field. They resonate at the they are a shielding zone and they resonate at the low frequency or maybe high magnetic field. So here in this region, it is opposes the applied magnetic field. So similarly, when we take some of the examples like other double bonds and triple bonds. So here, this zone is shielding zone. We get a 5 to 7 ppm or so, and these protons are de-shielding here. Also shielding here. So shielding zones, they will come very close to the TMS waveform, that means right side of the wave. And de-shielding, they will come at the high ppm or low frequency. So if we can measure all these induced magnetic fields, then we can work backwards and get the structure. So what is the basic criteria to become NMR active? So we cannot get NMR signals for all the molecules. Let us say for all the nuclei. So to have a basic nature, that means basic principles is you need to have two things. Like first is the nuclear spin, and second one is the natural abundance. So what is the nuclear spin? So if you take mass, mass is the total number of neutrons and protons. If you have a mass of any isotope of any element, if you have a even mass, that means your proton and neutrons are both even, then you have a net magnetic nuclear spin will be zero. So these are all not NMR observable nucleus. For example, if you take a carbon is isotopes like C12 isotope, C13 isotope, and C14 which is radioactive. So if you take carbon 2 isotopes like C12 and C13, and C12 is not an NMR active, so even though its natural abundance is around 99%, but C13 is an NMR active, so with a nuclear spin of half, but its natural abundance is only 1%. So having natural abundance is not only enough, but you should have a nuclear spin also. So similarly, in the case of oxygen, equal number of neutrons and protons, which makes it NMR inactive. So if you take another case like mass and the protons are uneven in nature, then you have a net nuclear butterfly movement. So these also NMR active, but the problem here is you get a broad lines. So but still you can see the NMR signals in these kind of elements. The major, the best nucleus which are studies for the NMR is with the nuclear spin of half. For example, in the case of proton, carbon, 1H proton, 13C proton, 13C, and then 15 like this. So these nuclei, they have their mass is uneven, and they have a nuclear spin of half, 3/2 or 5/2. So these they will get a very sharp lines, and then these are also very good for NMR studies. And you can do the quadrupolar movement also, where like the nucleus like boron, aluminum, all those things, but you will get a very broad lines. So So this is the table which tells you, which are the nucleus NMR active. So if you look at like unpaired protons and number of unpaired neutrons here in this table, all these they have a net spin of like proton it has off, and then there is the deuterium also it has a net spin of off. And similarly, we have all the neutrons we have explained here. So these are the basic principles to become NMR active. So what are the nucleus can be studied? So if you look at this periodic table, and most of the nucleus are NMR active. So they have a different spins, which you can see here the color codes here. So these are with the nucleus spin off like the proton and the C13 and 15. They are all the half nuclear spins. Of course, their natural abundance is different for nuclei, and with the nucleus spin 1, and then similarly you can see all. So most of the elements you can be studied from the element from the NMR. So nearly almost all the elements they have the angular momentum. So they are NMR active nucleus. So how do we observe the NMR signal? So if you place a sample in the magnetic field, if you have a nuclei without the external magnetic field, like that means the spins, the nuclear spins, they orient in a random nature, like as you showed in this left side of the figure. Here, this is the absence of the magnetic field. If you look at the sum of the magnetic moments, for macroscopic magnetization, which is a net magnetization is 0 in this case. If the same sample is taken into the magnetic field, that means if you place the sample inside the magnet, whether it is a permanent electro or maybe superconducting magnet or any field kind of magnet, these spins they orient either in a parallel or anti-parallel to the applied magnetic field. If you say this is applied magnetic field, then either they will orient parallel or anti-parallel. So they have here we have a net magnetization, non-zero net magnetization here. So this is enough to get an NMR signal. So when we put the sample in the magnetic field, we get a net magnetization moment. Then we need to disrupt this magnetic field. So that means we have to apply some radio frequency to increase nuclear lower energy magnetic field. So how they split this energy level when if you talk about the G1 energy levels, if you have a nuclear spin of off, they split into two energy levels, upper energy level and lower energy levels. And this energy level difference, like that type, if you take, like it's a gamma expressed to P naught. Whereas gamma is the gyromagnetic ratio of the nucleus, and this is depending on it's an intrinsic property of the nuclei, like proton, carbon, which proton has a very highest gamma, and then carbon is a 1/4 of that. So it directly depends on the gamma and also that P naught, that applied magnetic field. So in the next slides, I will show you how this energy level is spread and then how it is contributing the sensitivity in coming slides. The number of nucleus and then with magnetic field. So if you normally in the NMR terminology we say it's a Larmor frequency. That means that when we put the magnetic samples in the magnetic field, these they behave like a bar magnets, and which align they are to the applied magnetic field. So these magnetic moments they persist around the applied magnetic field like this, and this persistent frequency what we say is a Larmor frequency. So how do we define this Larmor frequency? If you let us say it's simple equation like omega is equal to gamma P naught. As I earlier explained, gamma is the gyromagnetic ratio. This is the applied magnetic field. And take an example of the proton. Proton is a gamma of highest, and then with the 11 Tesla of the magnetic field, applied magnetic field, it resonates at 500 megahertz. Normally we say in the frequencies like 400, 500 like this, and this 500 megahertz is nothing but your 11 Tesla of the magnetic field. At the same frequency, because of the gamma, 1/4 of gamma, carbon is 125 megahertz. So similarly, you have to check with other nucleus also. So this shows that we have various frequencies. If we measure these frequencies, then we can determine the structure of the molecule. So when we place a sample in the magnetic field, these pins will be at the bottom. So when we apply a frequency, so they will go into the upper magnetic. So that means they resonate each other. So this is called a resonance. So if they stay here, we don't nothing will happen. That means we are not able to receive the signal. So then they will not stay here for longer. Then they lose the energy and they will come down to the original ground state again. So while coming down, So we detect the signal as a time-driven signal. So that's what we hear. When we apply the radio field, we come to the XY plane. In this XY plane, we have receivers. This will be detected as a time-driven signal. So these split into the time. So this time-driven signal. So if we try Fourier transform of this time-driven signal, then we will get a frequency domain. This is the time versus intensity, and here frequency versus the intensity. So in this figure we have explained. That means what we say usually 90 degree. That means we flip from the x direction to the x plane like completely, and then we can that the signal will not be stay here for longer. It will lose the energy by along the xy and relax back to the vertical position with the T1 and T2 relaxation process. So this is Fourier transform to get a frequency domain spectrum. So this intensity of the signal, it depends on the nature of the compound. If you have a long relaxation delay, then you will get sharp signals, and if you have a short relaxation delay, you will get the sharp broad rays. So if you look at this intensity of these two, even though they are upon the number of protons one. So here we have a long relaxation delay. We have a sharp initial rise here, and you have a short FID. FID is free injection delay. If you do the full transformation of this, then we get a very broad signals. So, but please note that here both both signals are only one proton. If you integrate from this place to this place, you should get the same value and integrate from the here to here. That is whole range. So usually earlier we used to say it is like continuous wave and mass spectrometer. That means where we used to vary the frequency, then we should keep the magnetic field constant. So in the modern spectrometers, what we do, we keep the magnetic field constant, and then we vary the frequency. So now in the earlier we used to call it as snail NMR. We used to change the frequencies. So to normally this Fourier transformation NMR grids analogy is given to this piano of the instrument. Let us take we have 7 keys of the piano, and if you press each 7 keys one by one, like then you will get a unique individual frequencies separately. And let us say you press all the 7 keys together, then you are not able to differentiate the frequency of all the 7 keys. Then you will get some noise. Then this noise you feed into the computer and do the Fourier transform. This is the, let us say you bang all the 7 keys together, and if you feed this noise into the computer and you do the Fourier transformation, you will get frequency of all the individual keys in the separately. That's what we do in the same technology we are using in the NMR instrument. So earlier what we used to do, we used to vary the frequency of each, we used to try to exert each signal at the different frequency. But instead of that, what we are doing, we are exerting 88 together, like this is from 0 to 20 ppm in the case of proton, we exert together, and we get the signal, and we do the Fourier transformation, and we get the individual signals. This is the concept of Fourier transformation NMR. For this, he got the Nobel Prize in 1991. So as I told you, this energy level splitting is on the gamma and then applied magnetic field. You can see this here. So this graph shows that this is the energy level versus the applied magnetic field. So at the lower magnetic field, lower applied magnetic field, we have a spins, and that is, let us take like proton at the highest gamma proton. We have 4 spins at the lower energy and 3 spins at the upper energy. That means we have only 1 spin. So we get a less intensity. When you go for the next magnetic field, we have 2 spins excess. Similarly, when you go for the very high field magnets, and we have almost more intensity here. That means your energy level is split more. That to get the better intensity sensitivity, we go for the high magnetic. And not only the magnetic field, and the gamma also plays a role here. See, for the if let us take, this is the proton energy difference, and the same carbon it is less. That means 1/4 of that. And for the same magnetic field, and the same magnetic field, if you take the nitrogen, it is almost 1/10. So it's we have a disadvantage of obtaining a carbon or nitrogen signal to both. for the with respect to the gamma and with respect to the natural abundance. So that's why we need more time to acquire these signals. So if you let's take it 400 megahertz, that means if you take if you talk in the sense of the magnetic field, which you say 9.4 Tesla, and at 400 megahertz, if the what we say proton is range at 400, similarly carbon at 100 and nitrogen is at 110, 40 megahertz. So here you can see that time scale, the proton, fluorine, phosphorus, carbon, and nitrogen, silver, like this. So, but we cannot observe all the signals together because we cannot excite everything full of voltage. You need power in megawatts if you want to excite. So, what we do normally, we tune into the signal frequency. Like when we want to proton, we will tune into proton frequency and we will get the signals. Similarly, for the fluorine, phosphorus, and carbon, whatever place we want, we will tune into that particular frequency and we will get the signals. So how this intensity relates, it can be explained in the higher and lower energy level by this Boson equation. This is n alpha by n beta, which is equal to E per minus delta K. Delta E is the energy level, that's what I told. T is the temperature and K is the working pressure. So at the room temperature, if you take let us say of around 4 million of the spins, then we get only 100 at the lower range. So that means, so what we say is NMR is a very insensitive when compared to the other techniques. That's why we need a more sample here in NMR or longer time or maybe higher magnetic fields. So the NMR is a insensitive techniques. That's the reason. So not only that this one, and then we have another disadvantage of natural abundance, and that is also causing, as I explained earlier, that natural atoms of the proton which is 99, and carbon is 1.1 and nitrogen is 0.9. We have highest here. So the carbon is still less and nitrogen is less. There is another factors which is influencing the sensitivity of the systems and the natural abundance. And so you need to you can even label these compounds to 100% in the case of like proteins and peptides. Usually they do protein studies. They do the labeling of the C13. They do 100% and they will get full signal to increase intensity. And similarly for the coordination compounds, people will do the isotopic labeling of the input. So that magnetic fields, this is also directly proportional to the magnetic field, the sensitivity. It can be enhanced by the by increasing the magnetic field. So if you look at the spectrum, so if you want to double the sensitivity, so I mean, if you let us say if you have an instrument of double frequency like 400 to 800 megahertz, so we can we get a 3 times of the instrument with the signal to noise ratio. We go to relation with this equation. So we have for the here the experiment is that and then signal to noise ratio. It is photons. If the if your signal to noise ratio is double, then your experimental time will be reduced by 4. So it's like it goes by 1:4. So and then if you look at this delta and then this Earth scale. Normally, what we say chemicals if they are field dependent, and then Jacob peaks are field independent. So this statement can be justified here because if you look at the any NMR signals in the delta ppm, you see always at the same ppm, like whether it's a 400, 500, 1 gigahertz, they all resonate at the same ppm here, same ppm. That's what we showed in the ratio figure. If you look at the same signals in the Earth scale, okay. So if you look at the 900 megahertz, the same signals, they will separate very easily here. At 250 megahertz, almost they are very close by. So this is another factor you need to consider when you are assembling the sample. For example, here that same delta ppm of ppm difference in 60 megahertz, we get in the ppm scale we get a same difference in ppm. But when you go for the Earth scale, you look at here, for 60 it's a 210 hertz and for 100 it's a 350 hertz. That's what it's explained here. In the same case, you can take it here. So this is the delta scale and then Earth scale, which which is explained here, 0 to 10 ppm and 0 to 10 ppm. 60 megahertz is maximum, you get about 600 hertz, and in 300 megahertz you get a 3000 hertz, close to 3 kilohertz. So you get a very good chemical shift dispersion when you go for the higher and higher frequency. So some of this experiments has been explained in this chemical shift dispersion. If you take this sample at 5.2 ppm of this particular sample at 250 megahertz, they are all almost close. You know, you are not able to differentiate anything. The same signal, if you take it into a at higher 600 megahertz, you see how they are well dispersed in where you get high resolution as well as the high sensitivity in this high frequency. Yeah, this is another one of the big molecule explained in this by using these different frequencies like 400 megahertz, it's full clumsy. When you go for the 600 megahertz, it's little better. But the same sample, if you take it at 900 megahertz, you look at signal bunch. They are all highly separated. Even some of the things are there explained from this bunch to here. They are all well separated. These signals, these it's all separated here. So this is the tire fluid, the chemical shift dispersion. We have a more chemical shift dispersion. And normally in the NMR we say the strongly coupled spin system and weakly coupled spin system. So this is the slide which explains you the this is simulated spectra with a different magnetic field. So if you take, let us say, like the ethanol spectrum of CH3 and CH2, forget about HCl, let us say CH3, you will get a triplet, and CH2, you will get a quartet if you neglect the OH contribution. At 300 megahertz, you get a triplet and quartet. At 200 megahertz, you will also almost get it. But when you come to 60 hertz megahertz, it will be like will become a complicated strongly coupled spin system. At 10 megahertz, almost you are not able to differentiate the signals at all. So this is the concept. This simulation spectra explains the strongly coupled spin system, how the strongly coupled spin system at lower magnetic field will become a weakly coupled spin system at high. So this is one of the things, one of the slides which explains the strongly and weakly coupled spin system. They are well separated here at 600 megahertz, but 100 megahertz they are very strongly coupled. There is very crowded signals. So this is how the magnet magnet technology has been developed up to I think up to 60s. You know, we have iron magnets, and later 70s or so. Now we have up to 1.2 gigahertz of conducting magnet technology is available. So why we went from the iron magnet to the superconductor means, you know, up to 100 megahertz the current process magnetic strength, if you look at, you know, it's linearly increased. Once it goes to the 100 megahertz, you know, whatever current you put in it will get saturated. So that's why we went for the superconducting technology, where you can put more current to get the more magnetic field. So this is the Brooker's milestone in the superconducting technology. And this is the spectrometers. So if you look at, this is the magnetic, how the magnet works. It's iron magnet, and this is the permanent magnet. It's for 80 now, I think. And this is they are all superconducting magnet. They are, this is 400 and 250 and 80. So this is the highest field available in India, as my colleague explained in his presentation. The world's presently commercially available is 1.2 gigahertz, which is 200 megahertz. If you look at the sensitivity in 60s and now in 2000, you know, for the, if you get almost like 500 times sensitivity, because this as the technology increased, you know, sensitivity is increased. So this slide already my colleagues showed here. I think I just skipped this here. This same slide. So this is the superconducting magnet, how it works. So what are the factors affecting this NMR magnetic field? Look at several factors, and the main thing is the chemical shift interaction between the electronic cloud, J through the bond, dipolar through space, and quarter polar T1 into direction. These are some of the factors which affect your NMR signal. So the main, after all, what we get from the NMR is that this slide will explain very quickly. That you get what are the information you get from the NMR spectrum? You get first the chemical set, which tells you the number of different type of the nuclei. And by integrating the different type of the nuclei, you get how many different type of the nuclei are there. And from the spin pattern, you get the what kind of the neighboring nuclei you have. And from the nature of the bond, you can get from the Gauge chart, and then connectivity, proton-proton connectivity, you can get from the experiments called like Koji and toxic correlative spectroscopy, total correlative spectroscopy. And proton C13 connectivity can be explained by these kind of experiments like HS correlation or color. And nowadays, what we say is HSQCH and this kind of experiments. And C13 connectivity can be done by using this experiment. And number of protons attached to the carbon they will get from this kind of experiment. And spatial proximity we get from the Noji and Doji kind of experiments. And we get there are a lot of many other things also like the Doji and so many experiments are there. So this is a simple slide, how you get NMR signals, and it's very basic one. If you let us water, you have only one type of proton. Now you have two types of signals. Two signals, and in that ethanol we will have three types, and we will have like this. So not only different kind of the protons, you have this one with the signals. So you have if you integrate these signals, so you will get how many different kind of the signals also it will tell you. So and then not only that, when you expand these signals, you get what kind of the neighboring nucleus you have, it will tell. If you have one proton, you get doublet. If you have three protons, you get like this, and it can be interpreted from the both sides. And another factor, this is scalar coupling, which is arises from because of the neighboring nuclei, and different nuclei have a different kind of the scalar coupling. Here I have given values here. So we have information, but these complex signals they will be having with the spline splitting, but we get a reduced intensity. For example, in the case of carbon, if you get a coupled one instead of the one methyl, you get a quadrat, which is a very complex in nature. That's the reason why we do that. So this is how this splitting pattern happens. It will follow the Pascal triangle, that the intensity of this 1:1, 1:2. So that's how we can say how the intensity goes up. And this chemical shifts also, they are directly depending on the electronegativity. If the electronegativity is more, then you have a highly de-shielding effect, and you go to low field or high field. De-shielding effect, higher electronegativity is higher de-shielding effect. So that's why we use the TMS as the internal standard, because it's highly shielded. All the 12 protons are highly shielded. It represents at 0 ppm. We reference it to be 0, and the rest they will present at the downfield. Maybe some of the effect in the high field, which is it's highly inert. It's not chemically. It don't do any chemical reactions with the sample. It's chemically inert. So in some of the anisotropic effects, if you look at, so like if you go from single bond, double bond, and triple bond, we expect like this, from high field to low field. But in principle, it's not the case, because we have the low field of the triple bond, we get at 2 to 3 ppm. So this is explained by using this anisotropic effect. So in this case, the protons they lie here along with the equivalent field. That means they opposes the applied magnetic field. That's why they come at the low field. So they have a shielding effect. So these electrons are said to be protons. And similarly, the protons which are shielding zone, they will come at a high ppm, and here and then the de-shielding zone, they will come at the low field or high frequency. Here you can see 0.4 and 1.4 ppm, and ideally proton will get at 9 ppm. So these are like acetone and benzene signals, why they are coming at high and low field. And here you can look at the annulate. Here, the protons inside the ring, they will come at around -3 ppm. Whereas protons at outside the ring, they will come at again 9 ppm. There is a nearly 12 ppm difference in this molecule. We have examples like this. You can majorly. These are all shielded. So shielded will come at close to TMS signals, and deshielded comes at the low field, ER also in this molecules. Outside deshielding and inside shielding. So this is where the different typical chemical scale from the different for the proton and the carbon. And you can chart this chart you can use literature available, you can get it from anywhere. So this is the different functional group where they resonate. And this is a slide which will explain in the field of NMR peptide and proteins. Normally people will do this Koji, Toxi, Mochi, and Koji kind of experiments. And Koji, which will give only the crossings between the 3 bond 3 GCHH here. You will get only the Koji kind of experiments. And if you want a longer relations, longer correlations, and you have to go to the total correlation spectroscopy, like it's called Toxi. And similarly, we have a different kind of no-zero. It happens through space only. It's intramolecular, only through space. So we'll get a no-G and no-G kind of experiments through space. And this is the one of the proton M15 HSQC of the protein, which is up almost like you get a through space again, proton scalar particles. So you can see many signals. And you can extend this technique to the 3D also. This is one of the examples which shows the 3D molecule. So one side is proton, another side carbon, and another side is nitrogen. Here it's 1 is 15 and 6. 3D and 4D, many dimensions also. Now it is. And if you look at the solids applications, and this is the how the solid line set looks like with the static mode. When you this is the solution, the same sample in the solid state like this it comes, and it's because of the dipolar coupling. So you need to remove this dipolar coupling. For that, you need to spin the sample at 54.7 kilohertz at very high spin speed. My colleagues said, it is almost like some 5 kilohertz up to 111 kilohertz nowadays. We have technology. You can spin the sample at such a frequency. So we by spinning at this angle, we are making this term 0, so that our dipolar contribution will become 0. So these are some of the probes already my colleague showed this slide, and this is how the spectral looks. The static spectrum, that means without spinning, and it's spinning at 3 kilohertz and spinning at 5 kilohertz. So you can easily see the signals at high spinning speed. And this is another 2D experiment for the solid state applications. You can check here. And this NMR applications has been given, as I said, they got Nobel Prize for the medicine. So here you have we apply the gradient along with any like brain or whatever, or any part of the body, and the water signals at the different places, they will get a different signals because of the gradient. Let us say there is, if I scan whole brain, if there is any tumor inside the brain, so there in that place, I don't get a water signal. So I have a different signals in that. So by projecting, by back calculation, they will say where is which part of the brain is affected. This is non-invasive, so you don't need to inject anything here. That's how this MRI technology is working. And this is some of the images of the MRI. So if certain parts of the brain damaged, it can easily identify. So in you can have a number of applications in the metabolites. So if you take, let us say, biological fluids like urine or serum, anything. So this urine, which has a lot of metabolites, close to 160, 170 metabolites, which has different amino acids, organic compounds, and then so many things. Now here, all the metabolites from using the NMR, you can detect and then you can quantify also. So it has a very good applications in the field of medicine. When they want to do the when they are undertaking these operations, they have to control certain molecules in the body. So that it's very useful. These NMR. So these are the NMR spectrum of the different biological fluids you can see here. So all these molecules, so many metabolites, close to 160, 170 metabolites. And only in medicine we have a food profiling also. So you can profile the fruit by using the NMR technology, and which is as my colleague told you, because of this high dynamic range. So all kind of the metabolites you can constraints in the food grades you can identify the quantifiable as well as the you can identify as well as the quantify. So, for example, this is the one of the spectra of apple juice. You can quantify it. This is the different 50 duplicate of the apple juice. If you see, they are highly reproducible. So, if there is any mixture, and then you can get the sequence. So that that's how you can do the quality check of the apple juice. This is the how we do the food treatment. We can have a targeted and non-targeted. If you have some adulteration in that molecule, then we have, if we lie outside this region, then it can be easily detected, and which is the sample which lies in this stage is accepted. So this is how this food screen only works. And this is some of the models we have. This targeted and targeted. This is the targeted. And we have a lot of database for this juice screening and other things. And latest, this one what we have is food screening is in the honey profiling, because the honey is the majorly used in nowadays, and because of this large huge demand, people are making a lot of adulteration in the honey by adding the sugar, maybe with the unripe honey and all those things. So these are the parameters can be easily identified by the NMR. So it's one of the spectrum of honey. So where you can identify different parameters, close to some 60%. So they are all unique to each sample. They are very highly reproducible. So observations of the several hundreds of the compounds you can make it. And this is the non-targeted screening of the honey. If honey sample and if lies apart from this zone, then it can easily detect that it can be adulterated. And this is the report of honey analysis. We have some report. Just I am showing is a sample one. One of the page. So we have the what is the value what you get and what is the inter quantization. If it lies in this stage, and we say that it's an is positive, otherwise we will get a red mark. So this is the nowadays a lot of applications of the. We have a lot of large database for the honey all over the world. So we have some couple of honey spectrometers in India. So these are the some of the applications I want to cover, and then the basics. So sorry for the technical disturbance between. So that's all. Thank you very much. Thank you for giving me opportunity. Hello.
Yes. Thank you, sir. Thank you very much. So, participants, if you have any questions regarding the topic, you can ask to Chandrasekhar sir or Dr. Anil Kumar sir.
Yeah, sure.
Yeah. Any questions from participant side? Okay. If not, then we'll proceed. So it was a great opportunity, sir, for our participants to have such a nice and informative sessions, both from Dr. Chandrasekhar and Dr. Anil Kumar sir. Both have revealed so many aspects of NMR in very smooth and easy manner. Thank you for your valuable guidance, sir. On behalf of Government College of Pharmacy, I extend my sincere thanks to Dr. Chandrasekhar and Dr. Anil Kumar sir for delivering such a nice and informative sessions for our participants. And I would like to request our FDP coordinator, Dr. Charde sir, to present the certificate of appreciation to Dr. Chandrasekhar sir.
Sir, please accept certificate, virtual certificate from our side.
Okay, and the certificate
Thank
of
you, sir.
appreciation for.
Thank you very much. I'm sorry for technical issues, so which is behind my
No
control.
problem, sir. No problem.
Thanks for.
Yes.
No,
Thank you,
Anil,
sir.
Thank you very much.
Thank you very much. Yeah.
thank you very much, sir.
Thank you, sir. So with this, we announce that today's session is concluded. Thank you very much.
There are some instruction for the participants. Tomorrow we have two sessions of Dr. Saranjit Singh sir and Dr. Bhupendra Singh sir. Bhupendra Singh Bhup sir in the morning. After lunch, we will have the online examination on quizzes. Everyone have to attend that examination, all the registered participants. And after that, we have valedictory function at 4 o'clock. So thank you very much. We'll meet in the morning. Thank you. Thank you, Chandrasekhar sir. Thank you, Anil sir. See you.
Thank you very much. Thank you very much for giving us an opportunity.
Thank you
Gonzalez
very
sir,
much.
shall
Sir.
we end? Yeah, thank you.
Yes, sir.
Yes, okay.